nuclear fusion, the process that ignites the stars and bathes our world in light, is often hailed as the holy grail of energy production, a clean and virtually limitless power source that could one day solve our planet's energy crisis. But its potential extends far beyond the confines of Earth. It is a promise whispered in the language of physics, a vision of humanity breaking free from the gravitational cradle of our homeworld and venturing into the vast, dark expanse of the cosmos. In the fiery heart of our sun, and in the cores of trillions of other stars across the universe, the alchemy of fusion is constantly at play. Under conditions of unimaginable pressure and temperature, the simplest and most abundant element, hydrogen, is forged into helium. In this process, a tiny fraction of the initial mass is not lost, but is converted into a colossal amount of energy. A conversion governed by Einstein's famous and elegant equation, E equals mc squared. This is the engine of the stars, the source of the energy that has sustained life on Earth for billions of years. And now, we stand on the threshold of harnessing this same cosmic fire, of building our own miniature stars to power not just our cities, but our starships. The dream of fusion propulsion is the dream of speed. If we can build a reactor, a magnetic bottle capable of containing a star's core, and install it on a spacecraft, the possibilities are breathtaking. We could achieve velocities that are currently the stuff of science fiction, speeds that would shrink the vast distances of our solar system, transforming a multi-year journey to the outer planets into a matter of months, or a perilous, months-long voyage to Mars into a swift, weeks-long transit. This is not just a matter of convenience. It is a matter of life and death for human exploration. Shorter travel times mean less exposure for our astronauts to the debilitating effects of deep space, the constant bombardment of cosmic radiation, the muscle and bone decay of prolonged weightlessness, and the profound psychological challenges of isolation in the void. Fusion propulsion is not just about getting there faster, it is about getting there and getting back, alive. The designs for such a craft are no longer just sketches on a napkin. They are the subject of serious, ongoing research. The fusion rocket, in its various forms, is a concept that has been explored for decades. In one version, the immense energy from a controlled fusion reaction is used to heat a propellant, like liquid hydrogen, to an incredible temperature, expelling it from a nozzle at a velocity far exceeding that of any chemical rocket. This would allow for a continuous, gentle, but relentless acceleration, a constant push that, over time, would build up to incredible speeds. Imagine a spacecraft that is not a slave to the brief, violent bursts of a chemical engine, followed by long periods of helpless coasting, but is a master of its own trajectory, able to accelerate for half its journey and then turn around and decelerate for the other half, arriving at its destination with a grace and efficiency that is currently unimaginable. The fuel for this cosmic journey is another of fusion's great promises. The primary ingredients for the most studied fusion reactions are isotopes of hydrogen, namely deuterium and tritium. Deuterium, a stable and harmless isotope, is a natural and abundant component of all the water on Earth. A single gallon of seawater contains enough deuterium to produce the energy equivalent of 300 gallons of gasoline. Tritium, a radioactive isotope, is much rarer, but it can be bred from a common and abundant light metal, lithium. The Earth has vast reserves of lithium, and it is also thought to be present in significant quantities on the Moon and on asteroids. This means that the fuel for our interplanetary voyages is not a rare, exotic, or finite resource that we must painstakingly haul up from Earth's deep gravity well. It is a resource that is, for all practical purposes, inexhaustible and potentially available in situ, right where we need it in space. This is a paradigm shift in the logistics of space exploration, a future where we can establish fusion-powered outposts on the Moon or Mars, outposts that can refuel their own spacecraft by mining the local resources, is a future where humanity is no longer tethered to its home planet. It is a future where we become a truly spacefaring species, with the freedom to explore, to settle, and to build a new, multiplanetary civilization. This is the grand and beautiful vision that fusion propulsion offers. But it is a vision that is still on a distant horizon. The challenges of achieving controlled, sustained nuclear fusion, even here on Earth under the most controlled laboratory conditions, are immense. For decades, it has been a goal that has seemed perpetually 30 years away. But in recent years, something has shifted with the construction of massive international projects like ITER in France, and with a new wave of innovation from a host of private fusion companies. A tangible sense of progress is in the air. We are, perhaps, closer than ever to bottling a star. And in doing so, to unlocking the key to our own cosmic future. The journey will be long, the challenges will be great. But the prize is nothing less than the stars themselves. The quest to replicate the power of a star here on Earth is one of the most ambitious and challenging scientific endeavors ever undertaken by humanity. It is a journey that has spanned decades, a global effort involving thousands of scientists and engineers, all driven by the promise of a clean, safe, and virtually limitless source of energy. At the heart of this quest lies a fundamental challenge: how to create and control a substance that is hotter than the core of the sun. For fusion to occur, we must heat a fuel of light atomic nuclei, typically deuterium and tritium, to a temperature of over 150 million degrees Celsius. At these extreme temperatures, the fuel is no longer a gas, but a plasma, a superheated, electrically charged soup of ions and electrons, often described as the fourth state of matter. No physical container can withstand such temperatures. Any material would be instantly vaporized. And so, physicists have had to become masters of the intangible, learning to build bottles out of invisible forces. The leading approach to this is magnetic confinement, in a device called a tokamak. A powerful and complex set of magnetic fields is used to suspend the hot plasma in a donut-shaped vacuum chamber, holding it away from the chamber walls. The plasma, being made of charged particles, is forced to spiral along the magnetic field lines, trapped in a magnetic cage. This is a delicate and unforgiving dance. The plasma is a notoriously unstable and turbulent fluid, and any small instability, any flicker in the magnetic fields, can cause it to touch the walls, instantly cooling it down and quenching the fusion reaction. For decades, the story of magnetic confinement fusion has been a story of incremental progress, of learning to tame this stellar fire, of building larger and more powerful machines that can hold the plasma for longer times and at higher temperatures. An alternative approach is inertial confinement. Instead of holding the plasma in a steady state, this method seeks to create the conditions for fusion in a brief, fleeting, and incredibly violent instant. In a facility like the National Ignition Facility in California, a tiny, BB-sized pellet of fusion fuel is blasted from all sides by the world's most powerful lasers. The intense energy from the lasers causes the outer layer of the pellet to explode outwards, and by Newton's third law, this creates an inward-moving shockwave, a rocket-like implosion that compresses the fuel to a density and temperature far exceeding that of the sun's core. The goal is to create a tiny, man-made star that exists for just a few billionths of a second, but in that instant releases a burst of fusion energy. Both of these approaches have been on a long, slow, and often frustrating journey. For decades, the holy grail of fusion research has been net energy gain, or ignition, the point at which a fusion reaction produces more energy than is required to heat and confine the fuel in the first place. It is the point where the fire becomes self-sustaining, And after more than half a century of effort, we are finally on the cusp of reaching this milestone. The International Thermonuclear Experimental Reactor ITER, currently under construction in the south of France, is a massive, global collaboration, a testament to what humanity can achieve when it unites to tackle a grand challenge. ITER is a tokamak of unprecedented scale and power, designed to be the first fusion device in history to produce a significant net energy gain, generating 10 times more power than is put in to heat the plasma. It will not be a commercial power plant, but it is the crucial penultimate step, the scientific and technological demonstration that fusion power on a large, practical scale is possible. ITER is scheduled to begin its first experiments in the coming years, and the results will be a pivotal moment for the future of energy on Earth and for the future of our journey into space. The potential benefits of succeeding in this quest are almost impossible to overstate. Unlike fossil fuels, fusion produces no greenhouse gases, no pollutants that cause acid rain or smog. Unlike nuclear fission, the process used in today's nuclear power plants, fusion produces no long-lived, high-level radioactive waste. The primary byproduct of the deuterium-tritium reaction is harmless helium. While the reactor structure itself will become activated by the high-energy neutrons produced in the reaction, this radioactivity is much less intense and has a much shorter half-life than the waste from a fission reactor. And the fuel is abundant. The deuterium can be extracted from ordinary water, and the tritium can be bred from lithium, a common element found in the Earth's crust and in seawater. A single laptop battery contains enough lithium to, when combined with the deuterium from half a bathtub of water, produce the same amount of energy as 70 tons of coal. This is the promise that keeps the fusion community striving. The vision of a future powered by the same clean, safe, and sustainable energy source that powers the stars. It is a vision that requires patience, persistence, and a deep appreciation for the immense challenges involved. But it is a vision that is slowly and steadily coming into focus. The story of nuclear energy is a tale of two very different processes, two opposing paths to unlocking the immense power that is bound up in the heart of the atom. It is the story of fission and fusion, of splitting the heavy and merging the light. Nuclear fission, the process that powers our current fleet of nuclear power plants, is a process of division. It begins with a heavy, unstable atomic nucleus, typically uranium-235 or plutonium-239. When this nucleus is struck by a neutron, it can be induced to split, or fission, into two smaller, lighter nuclei. This process releases a tremendous amount of energy, along with 2 or 3 additional neutrons. These newly released neutrons can then go on to strike other heavy nuclei, triggering a chain reaction, a self-sustaining cascade of fission events that can be controlled to produce a steady stream of heat, which is then used to generate electricity. This is a powerful and, in many ways, elegant technology. It is a mature, reliable, and carbon-free source of baseload power. But it comes with significant and well-known drawbacks. The products of the fission reaction are a host of highly radioactive isotopes with long half-lives, a toxic legacy of nuclear waste that must be securely stored for thousands, and in some cases, hundreds of thousands of years. And while modern reactors have multiple, redundant safety systems, the potential for a catastrophic accident, a core meltdown that could release a devastating amount of radiation into the environment, as witnessed in the historical events of Chernobyl and Fukushima, remains a deep and persistent public concern. Nuclear fusion, on the other hand, is a process of unification. It is the process that powers the stars. It takes the lightest elements in the universe, typically isotopes of hydrogen like deuterium and tritium, and under conditions of extreme temperature and pressure, it forces them to merge, to fuse into a heavier nucleus, typically helium. As we have seen, this process also releases a colossal amount of energy, even more energy per unit of mass than fission. And it does so with a number of significant advantages. The fuel for fusion is abundant and widely available. The primary byproduct, helium, is a harmless, inert gas. And the fusion reaction itself is inherently safer than a fission chain reaction. It is not a chain reaction. It is a process that requires a constant, active input of energy and a precise set of extreme conditions to be sustained. If there is any disruption, any loss of confinement or temperature, the reaction simply stops. A meltdown in a fusion reactor is a physical impossibility. The fire simply goes out. But this inherent safety is also the source of its immense technological challenge. Creating and sustaining the conditions for fusion temperatures of over 100 million degrees Celsius, 100 times hotter than the core of the Sun, is an engineering problem of staggering difficulty. While fission can be achieved at relatively low temperatures, making it easier to control, fusion requires us to build a piece of a star here on Earth. This is the fundamental trade-off between the two technologies. Fission is the easier, but dirtier and potentially more dangerous path to nuclear energy. Fusion is the cleaner, safer, but far more difficult path. For over 70 years, we have walked the path of fission. But as the challenges of climate change and long-term waste disposal become more acute, the global scientific community is increasingly turning its attention and its resources to the more difficult, but ultimately more promising, path of fusion. The Great International Experiment, ITER, is a testament to this global shift. It is a monumental undertaking, a collaboration of nations that have set aside their political differences to work together on a single, shared goal to demonstrate the scientific and technological feasibility of fusion power on a commercial scale. The journey to practical fusion energy will be long and arduous, and success is not guaranteed. But if we can succeed, if we can learn to master the same cosmic fire that forged the elements and gave birth to our world, the payoff will be nothing less than the future of human civilization. The dream of harnessing fusion for space propulsion is not a new one. It is a concept that is almost as old as the atomic age itself, a vision that has captivated and inspired scientists and engineers for decades. From the very beginning of the space race, it was clear that the chemical rockets we were using to escape Earth's gravity, while powerful, were fundamentally limited. They were like the first sputtering steam engines of the Industrial Revolution, a magnificent achievement, but one that was inherently inefficient and constrained. The tyranny of the rocket equation, first derived by the Russian pioneer Konstantin Tsiolkovsky, dictates that for a chemical rocket, the vast majority of its initial mass must be fuel, leaving only a tiny fraction for the actual payload, the spacecraft and its crew. This makes long-distance, high-speed interplanetary travel incredibly difficult and expensive. It was clear that to truly open up the solar system, to become a spacefaring species, we would need a new kind of engine, one with a much higher specific impulse, a measure of its fuel efficiency. And nuclear energy was the obvious candidate. The first serious proposal for a nuclear-powered spacecraft was the audacious and somewhat terrifying Project Orion, initiated in the late 1950s. The concept was as simple as it was brutal. A massive spacecraft would be propelled by a series of small directional nuclear explosions detonated behind a large pusher plate, equipped with massive shock absorbers. Each blast would give the ship a powerful kick, accelerating it to incredible speeds. The concept was scientifically sound, and declassified documents show that it would have been technologically feasible. A full-scale Orion drive could have propelled a city-sized spacecraft to Mars and back in a matter of months, or even to the nearest stars in a journey of a little over a century. But the project was ultimately canceled, a victim of the Partial Nuclear Test Ban Treaty of 1963, which banned nuclear explosions in the atmosphere and in space, and of the profound and understandable safety and environmental concerns associated with launching a spacecraft armed with thousands of atomic bombs. But the dream of nuclear propulsion did not die. It simply shifted from the brute force of fission to the more elegant and ultimately more powerful promise of fusion. In the 1970s, the British Interplanetary Society conducted a detailed theoretical study of an unmanned interstellar probe called Project Daedalus. The Daedalus spacecraft was designed to be a two-stage fusion-powered vessel, capable of reaching Barnard's star, 6 light-years away, in a journey of just 50 years. Its engine was a marvel of theoretical engineering, an inertial confinement system that would fire a stream of tiny pellets of deuterium and helium-3 fuel into a reaction chamber, where they would be zapped by powerful electron beams, triggering a series of microfusion explosions. The hot plasma from these explosions would be directed by a powerful magnetic nozzle, generating a continuous and powerful thrust. Daedalus was a paper study, a magnificent and inspiring thought experiment, but it laid the groundwork for many of the more modern concepts of fusion propulsion. Today, researchers are exploring a wide range of different fusion engine designs. The direct fusion drive, a concept being developed at the Princeton Plasma Physics Laboratory, is a particularly elegant one. It uses a compact linear fusion reactor to create a hot plasma. But instead of using this plasma to heat a separate propellant, it uses a clever magnetic field configuration to direct some of the high-energy fusion products themselves out of the back of the engine, generating both thrust for propulsion and electricity to power the spacecraft. This dual-purpose design makes it incredibly efficient and versatile, capable of both high-thrust maneuvers for getting around the inner solar system quickly, and low-thrust, high-efficiency cruising for long-duration missions to the outer planets and beyond. Other concepts, like the magneto-inertial fusion drive, seek to combine the best aspects of both magnetic and inertial confinement, using a magnetic field to pre-compress the plasma before it is zapped by a powerful laser or particle beam. These hybrid systems could offer a path to a more compact, more efficient, and more technologically achievable fusion engine. The journey from these theoretical concepts and laboratory experiments to a working, flight-ready fusion engine is still a long one, but the progress is real, and the motivation is clear. The same cosmic fire that powers the sun is not just a potential source of clean energy for our planet. It is our ticket to the stars. It is the technology that could finally break the tyranny of the rocket equation and transform humanity from a species that is confined to a single, fragile world into a true, multiplanetary, and perhaps one day interstellar civilization. The fundamental principle that makes nuclear fusion such an incredibly potent source of energy is the concept of nuclear binding energy. This is the energy that holds the protons and neutrons together in the nucleus of an atom. When we look at the binding energy per nucleon, a proton or a neutron for all the different elements in the periodic table, we see a fascinating pattern. The binding energy is lowest for the lightest elements, like hydrogen. It then increases rapidly as we move to heavier elements, reaching a peak at iron and nickel. For elements heavier than iron, the binding energy per nucleon slowly decreases again. This curve of binding energy is the key to all nuclear energy. It tells us that we can release energy in two ways. We can take a very heavy, loosely bound nucleus like uranium and split it into lighter, more tightly bound nuclei. This is nuclear fission. Or we can take very light, very loosely bound nuclei, like hydrogen, and fuse them together to form a heavier, more tightly bound nucleus, like helium. This is nuclear fusion. And because the slope of the binding energy curve is much steeper on the light element side, the fusion of light nuclei releases far more energy per unit of mass than the fission of heavy nuclei. The most common fusion reaction in stars like our Sun is the proton-proton chain. In this multi-step process, 4 hydrogen nuclei, which are just single protons, are gradually fused together to form one helium nucleus, which consists of 2 protons and 2 neutrons. This process requires overcoming the immense electrostatic repulsion between the positively charged protons, a force known as the Coulomb barrier. In the core of a star, this is achieved through a combination of incredibly high temperatures, which give the protons a huge amount of kinetic energy, and incredibly high pressures, which force them into close proximity. And even then, the reaction is only possible because of the quantum mechanical phenomenon of tunneling, which allows a proton to occasionally pass through the Coulomb barrier even if it does not have enough energy to classically overcome it. The net result of the proton-proton chain is that 4 protons, with a combined mass of about 4.032 atomic mass units, are converted into one helium nucleus, with a mass of about 4.003 atomic mass units. The small difference in mass, about 0.7% of the original mass, is converted directly into a colossal amount of energy, according to Einstein's E equals mc squared. This is the energy that makes the stars shine. In more massive stars, a different fusion process, the carbon-nitrogen-oxygen CNO cycle, becomes the dominant source of energy. In this cycle, carbon, nitrogen, and oxygen act as catalysts to facilitate the fusion of hydrogen into helium. This process is much more temperature sensitive than the proton-proton chain, and it is what powers the brilliant blue-white stars that are much more massive than our Sun. The process of stellar nucleosynthesis does not stop at helium. As a star ages and its core runs out of hydrogen, it will begin to fuse helium into heavier elements, like carbon and oxygen. In the most massive stars, this process will continue, creating a series of nested, shell-like fusion zones, like the layers of an onion, forging progressively heavier elements all the way up to iron. The elements heavier than iron cannot be created through fusion in stars, as this process would consume energy rather than release it. These heavier elements are thought to be created in the cataclysmic explosions of supernova, where a massive influx of neutrons can be rapidly captured by the iron nuclei, building them up into the gold, the platinum, the uranium, and all the other heavy elements we find in the universe. The study of nuclear fusion is not just a quest for a new energy source. It is a journey into the heart of cosmic alchemy. It is the story of how the simple, primordial hydrogen and helium of the Big Bang were forged in the fiery furnaces of the stars, into the rich and diverse chemical tapestry of the universe, a tapestry that includes the very atoms that make up our planet, our bodies, and our brains. We are, in the most literal sense, the children of the stars, the products of a cosmic process of nuclear fusion that has been unfolding for billions of years. The human fascination with the cosmos is as old as our species itself. For our most ancient ancestors, the night sky was a source of wonder, of myth, and of practical knowledge. The regular, predictable motions of the sun, the moon, and the stars provided the first calendars, the first tools for navigation, the first sense of an ordered, comprehensible universe. In ancient Mesopotamia, the Babylonians were meticulous and systematic observers of the heavens. They created detailed star catalogs and developed sophisticated mathematical techniques to predict the motions of the planets and the timing of eclipses. Their astronomy was deeply intertwined with their religious and astrological beliefs, The celestial events were seen as omens, messages from the gods that could be deciphered to foretell the fate of kings and empires. The ancient Greeks inherited and transformed this Babylonian knowledge, moving from a purely predictive and mythological framework to a more philosophical and geometrical one. Thinkers like Pythagoras and Plato envisioned a cosmos governed by mathematical harmony, a music of the spheres. Aristotle, in the 4th century BC, developed a comprehensive and highly influential geocentric model of the universe, with the spherical Earth at its center, surrounded by a series of nested crystalline spheres that carried the moon, the sun, the planets, and the fixed stars. This model, later refined by Ptolemy in the 2nd century AD, would dominate Western astronomical thought for over 1400 years. The Great Shift, the Copernican Revolution, began in the 16th century with the Polish astronomer Nicholas Copernicus, who proposed a radical, and at the time, heretical, idea that the sun, not the Earth, was the center of the universe. This heliocentric model, while not immediately accepted, set in motion a chain of discoveries that would forever change our view of our place in the cosmos. In the early 17th century, the Italian astronomer Galileo Galilei, using one of the first telescopes, made a series of groundbreaking observations that provided powerful evidence for the Copernican model. He discovered the moons of Jupiter, proving that not everything orbited the Earth. He observed the phases of Venus, which could only be explained if Venus orbited the Sun. And he saw that the moon was not a perfect celestial sphere, but a world with mountains and craters, much like the Earth. At the same time, the German astronomer Johannes Kepler, through a painstaking analysis of the precise observational data of his predecessor, Tycho Brahe, discovered his 3 laws of planetary motion, showing that the planets move not in perfect circles, but in elliptical orbits, and that their speed varies as they orbit the Sun. The final piece of the classical puzzle was put in place by Sir Isaac Newton at the end of the 17th century. With his law of universal gravitation, Newton showed that the same force that makes an apple fall to the ground is what holds the moon in its orbit around the Earth, and the planets in their orbits around the Sun. It was a stunning and powerful unification, a single mathematical law that could explain both terrestrial and celestial motion. The 20th century brought another, even more profound, revolution. Albert Einstein's theories of special and general relativity completely overturned the Newtonian concepts of absolute space and time. He showed that space and time are not a static, passive background, but a dynamic, 4-dimensional continuum, space-time, that is curved and warped by the presence of matter and energy. At the same time, the development of quantum mechanics was revealing the strange, probabilistic, and counterintuitive nature of the subatomic world. And on the observational front, astronomers like Edwin Hubble, using the giant telescopes of the early 20th century, discovered that our Milky Way was not the entire universe, but just one of billions of other galaxies, and that these galaxies were all receding from us, a sign that the universe itself was expanding. This discovery led to the formulation of the Big Bang Theory, the idea that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since. The story of our understanding of the cosmos is a story of ever-expanding horizons, a story of the progressive decentering of humanity from a privileged position in the universe. It is a story that is driven by our insatiable curiosity, our desire to understand our origins, and our courage to follow the evidence, even when it leads us to conclusions that are unsettling, counterintuitive, and profoundly challenging to our most cherished beliefs. The scientific quest to understand the process of nuclear fusion, the cosmic fire that powers the stars, is a story that is deeply intertwined with the tumultuous history of the 20th century. It is a story that begins not with a search for clean energy, but with a quest to understand the most fundamental building blocks of matter and the forces that govern them. In the early decades of the 20th century, with the discovery of the atomic nucleus and the development of quantum mechanics, physicists began to grapple with a profound puzzle. What is the source of the sun's immense and long-lasting power? Chemical reactions, like the burning of coal, were far too inefficient to account for the sun's prodigious energy output over billions of years. In 1920, the British astrophysicist Sir Arthur Eddington was one of the first to propose that the answer might lie in the fusion of hydrogen into helium, a process that would convert a small amount of mass into a huge amount of energy. According to Einstein's newly discovered E equals mc squared. But it was the German-American physicist Hans Bethe who, in the late 1930s, worked out the detailed nuclear reactions that make this possible. He described the two primary fusion processes in stars: the proton-proton chain, which is dominant in stars like our Sun, and the CNO cycle, which is dominant in more massive stars. For this groundbreaking work, which laid the foundation for our entire understanding of stellar nucleosynthesis. Bethe was awarded the Nobel Prize in Physics in 1967, but as the world plunged into the Second World War, the focus of nuclear research shifted dramatically. The discovery of nuclear fission in 1938 had opened the door to the creation of the atomic bomb. And the top-secret Manhattan Project was launched in the United States to develop this terrifying new weapon. Many of the same physicists who had been pondering the secrets of the stars were now tasked with building a weapon of unprecedented destructive power. And in the post-war era, with the onset of the Cold War, this research continued, leading to the development of an even more powerful weapon, the hydrogen bomb, or thermonuclear bomb, a device that uses a fission explosion to trigger a much larger, uncontrolled fusion reaction. Scientists like Edward Teller and Stanislaw Ulam in the United States and Andrei Sakharov in the Soviet Union were the key figures in the development of this technology. It is a dark and complex irony that our first practical application of the same energy source that creates life-giving sunlight was in the creation of a weapon capable of ending all life on Earth. But alongside this military research, a parallel and more hopeful line of inquiry was beginning to emerge: the quest for controlled thermonuclear fusion for peaceful energy production. In the 1950s, scientists in the US, the UK, and the Soviet Union, working in secret, began to explore different ways to create and confine a hot plasma, the state of matter required for fusion. The Soviet team, led by Igor Tamm and Andrei Sakharov, developed a particularly promising magnetic confinement device called the tokamak. When the results of this research were declassified at the Atoms for Peace Conference in 1958, it ignited a new era of international collaboration in fusion research. The tokamak design proved to be the most effective at confining a stable, hot plasma, and it quickly became the dominant approach in the global fusion community. In the decades that followed, a series of progressively larger and more powerful tokamaks were built around the world, each one pushing the boundaries of plasma temperature, density, and confinement time. The joint European Torus JT in the UK, which began operation in the 1980s, was a major milestone, becoming the first device to produce a significant amount of fusion power, albeit for only a few seconds. Today, this global collaborative effort has culminated in the construction of ITER, the International Thermonuclear Experimental Reactor, in France. ITER is a monumental scientific and engineering project, a machine of unprecedented scale and complexity, designed to be the final, crucial step in demonstrating the scientific feasibility of fusion energy. The history of fusion research is a story of profound duality. It is a story that encompasses both the brightest hopes for a clean energy future and the darkest fears of nuclear annihilation. It is a story that has been shaped by both intense, secretive, nationalistic competition and open, global, scientific collaboration. And it is a story that is far from over. The path to practical fusion energy is still long and fraught with challenges, but it is a path that we must continue to walk, driven by the same curiosity that first led us to look up at the sun and wonder, how does it shine? Our understanding of nuclear fusion has evolved dramatically over the past century, moving from a purely theoretical concept to a tangible, experimental science that is on the verge of a major breakthrough. In the early 20th century, the discovery of the atom's structure and the equivalence of mass and energy set the stage. Albert Einstein's E equals mc squared, published in 1905, was the foundational insight, a simple but profound equation that revealed the immense energy locked within the nucleus of an atom. In the 1920s and 30s, the development of quantum mechanics and the discovery of the neutron provided the tools to understand the nuclear forces and the specific reactions that could release this energy. It was Hans Bethe's work in 1939 that provided the first detailed, quantitative model of how stars generate their energy through the fusion of hydrogen into helium. This was a triumph of theoretical astrophysics, a moment when we first truly understood the engine of the stars. The mid-20th century marked a pivotal shift from theory to experiment. The development of the hydrogen bomb during the Cold War was a grim and terrifying demonstration that uncontrolled fusion was possible. But it also spurred a parallel, and more hopeful, quest for controlled fusion. The 1950s saw the birth of the first experimental fusion devices, like the tokamak in the Soviet Union and the stellarator in the United States, both of which used powerful magnetic fields to try and confine a hot plasma. These early experiments were a process of trial and error, of learning to tame a substance that is inherently unstable and difficult to control. The journey was marked by slow, steady, but hard-won progress. Over the decades, our understanding of plasma physics, the complex science of superheated, ionized gases, has grown immensely. We have learned about the various instabilities that can plague a magnetically confined plasma, and we have developed sophisticated techniques to control them, using a combination of carefully shaped magnetic fields, powerful heating systems, and advanced computer modeling. The key parameters of a fusion plasma, its temperature, its density, and its energy confinement time, have all been steadily increasing, moving us ever closer to the goal of ignition. A key metric of this progress is the triple product, the product of the density, temperature, and confinement time, which must reach a certain critical value for a fusion reaction to become self-sustaining. The history of fusion research can be seen as a long, patient climb up the mountain of the triple product. The 1980s and 90s saw the construction of a new generation of large, international tokamaks, like JET in Europe and TFTR in the United States, which achieved plasma conditions that were tantalizingly close to break-even, the point where the fusion power produced is equal to the external power put in to heat the plasma. Now, in the 21st century, we are in the era of ITER. This massive, next-generation tokamak is designed to cross the final frontier to achieve a burning plasma, a state where the primary source of heating is the fusion reaction itself, and to produce a net energy gain of at least a factor of 10. The technological and engineering challenges are immense, from the development of powerful, large-scale superconducting magnets to the creation of materials that can withstand the intense neutron bombardment from the fusion reaction. In parallel with this mainstream, magnetic confinement research, the field of inertial confinement fusion has also made remarkable progress. The National Ignition Facility, NIF, in the United States, with its 192 giant laser beams, has, in recent years, achieved a major breakthrough, demonstrating, for the first time in a laboratory, a fusion reaction that produced more energy than was delivered to the fuel pellet by the lasers. This is a monumental scientific achievement, and while inertial confinement is still a long way from being a practical energy source, it is providing invaluable data and is opening up new avenues of research. Today, the landscape of fusion research is more vibrant and diverse than ever. A new wave of private companies, backed by significant venture capital, is exploring a wide range of innovative and alternative fusion concepts, from compact, high-field tokamaks to stellarators with complex, 3D printed magnetic coils, to novel approaches like magneto-inertial fusion. This infusion of new ideas, new technologies, and a new, more agile startup mentality is accelerating the pace of progress and creating a healthy and productive competition with the large, government-funded projects. Our understanding of fusion is no longer just a story of theoretical physics. It is a story of materials science, of advanced computing, of complex engineering, and of global collaboration. It is a story that is reaching a climax, a moment where a dream that has been pursued for nearly a century may finally be on the verge of becoming a reality. The dream of exploring the cosmos, of traveling beyond our own fragile world, is as old as humanity itself. But for most of our history, this dream was confined to the realms of myth, of fantasy, of science fiction. The 20th century, with the birth of the space age, began to turn this dream into a reality. But the reality has been a limited one, a reality constrained by the immense challenges of escaping Earth's gravity and traversing the vast, empty distances of the solar system. The history of space exploration is, in many ways, the history of our attempts to overcome these challenges, a story of an ever-evolving technology of propulsion. The journey began with the brute force of chemical rockets, the controlled explosions that have been the workhorse of the space age since its inception. From the V-2 rockets of the Second World War to the mighty Saturn V that took humanity to the moon, to the reusable Falcon 9 rockets of today, the fundamental principle has remained the same: the rapid combustion of a fuel and an oxidizer to produce a high-velocity jet of hot gas. Chemical rockets are capable of generating immense thrust, which is why they are still essential for lifting heavy payloads off the surface of the Earth. But they are also fundamentally inefficient. The tyranny of the rocket equation means that for any significant change in velocity, the vast majority of the rocket's mass must be propellant, leaving very little for the actual spacecraft. This makes long-distance, high-speed interplanetary travel incredibly challenging. To overcome this limitation, scientists and engineers began to explore other, more efficient, forms of propulsion. The 1960s saw the development of the first electric propulsion systems, like the ion thruster. An ion thruster works by using electricity, typically generated by solar panels, to ionize a propellant gas, like xenon, and then to accelerate these ions to an incredibly high velocity using electric or magnetic fields. The thrust produced by an ion engine is tiny, about the same as the weight of a sheet of paper. But because it is so incredibly fuel efficient, it can be operated continuously for months or even years, producing a slow, steady acceleration that can build up to very high speeds over time. Ion propulsion has been a game-changer for unmanned deep space missions, like NASA's Dawn mission to the asteroid belt and the European Space Agency's Bepi-Colombo mission to Mercury. It is the technology of the patient, robotic explorer. The dream of a more powerful and faster form of propulsion led to the exploration of nuclear energy. We have already discussed the audacious Project Orion, with its vision of a spacecraft propelled by nuclear bombs. A less dramatic but more technologically feasible concept is nuclear thermal propulsion. In a nuclear thermal rocket, a nuclear fission reactor is used to heat a liquid propellant, like hydrogen, to an incredibly high temperature before it is expelled through a nozzle. Because the hydrogen can be heated to a much higher temperature than is possible with a chemical reaction. A nuclear thermal rocket can be at least twice as efficient as the best chemical rockets, which would cut the travel time to Mars in half. This technology was extensively developed in the United States during the Rover/Nerva program from 1955 to 1973, and there is a renewed interest in it today as a potential near-term solution for enabling human missions to Mars. But the ultimate dream, the holy grail of propulsion, remains nuclear fusion. A fusion engine, as we have seen, would offer an even greater leap in performance, with a specific impulse that is orders of magnitude higher than even nuclear thermal propulsion. It is the technology that could truly open up the entire solar system to rapid, routine human exploration. And it is the only technology we can currently conceive of that could make interstellar travel a realistic possibility. The history of space propulsion is a story of a constant quest for higher efficiency, for a way to get more bang for our propellant buck. It is a story that has taken us from the controlled fire of chemical reactions to the gentle push of electric fields, to the harnessed power of the atom. And the next chapter in this story, the chapter that will be written in the coming decades, will be the story of our attempt to master the ultimate source of energy in the universe. The story of our quest to build a starship powered by the same cosmic fire that powers the stars themselves. The technical landscape of space exploration is a vast and intricate one, a complex tapestry woven from a multitude of different scientific and engineering disciplines. It is a world where the most abstract principles of physics meet the most practical challenges of building machines that can survive and operate in one of the harshest environments imaginable. At the most fundamental level, there is the science of astrodynamics or orbital mechanics, the celestial ballet governed by Kepler's laws and Newton's law of universal gravitation. Planning a mission to another planet is not as simple as pointing your rocket and firing. It is a complex process of calculating elliptical transfer orbits, of timing launch windows to coincide with the optimal alignment of the planets, and of using the gravitational pull of planets and moons in gravity assist maneuvers to gain speed and to shape the spacecraft's trajectory. This is the art of navigating the invisible currents and eddies of the solar system's gravitational field. Then there is the engineering of the launch vehicle itself. The rocket? This is a field of extremes. The forces involved in a rocket launch are immense, requiring structures that are both incredibly strong and incredibly lightweight. The temperatures in a rocket engine's combustion chamber can reach thousands of degrees, requiring advanced materials like nickel-based superalloys and sophisticated cooling systems. The guidance, navigation, and control systems of a rocket are a marvel of real-time computing, constantly measuring the rocket's position and orientation with a suite of sensors, like gyroscopes and accelerometers, and making thousands of tiny adjustments per second to the engine's thrust and gimbal to keep it on its precise trajectory. Once in space, the spacecraft itself is a self-contained robotic world, a marvel of systems engineering. The power subsystem, typically a combination of solar panels and rechargeable batteries, provides the electricity to run all the other systems. The thermal control subsystem, a complex network of radiators, heat pipes, and insulation, must keep the spacecraft's sensitive electronics within their narrow operating temperature range, protecting them from both the intense heat of direct sunlight and the extreme cold of deep space. The telecommunications subsystem, with its antennas and transponders, is the spacecraft's lifeline to Earth, responsible for sending back the precious scientific data and receiving commands from mission control. The avionics, or command and data handling system, is the spacecraft's brain. An onboard computer that executes the mission sequence, monitors the health of all the subsystems, and has the autonomy to put the spacecraft into a safe mode if something goes wrong. And then, of course, there are the scientific instruments themselves, the eyes and ears of the mission. These can be cameras that see in different wavelengths of light, from infrared to ultraviolet. They can be spectrometers that can analyze the chemical composition of a planet's atmosphere or the minerals on its surface. They can be magnetometers that can measure the magnetic field of a planet, or particle detectors that can study the solar wind and cosmic rays. Each of these instruments is a masterpiece of precision engineering, designed to perform a specific scientific task with incredible accuracy and reliability, often for many years, in the unforgiving vacuum of space. The technical world of space exploration is a world of immense complexity, a world where 1,000 different systems must all work together perfectly for a mission to succeed. It is a world that requires a unique blend of scientific vision, of engineering ingenuity, and of meticulous, painstaking attention to detail. It is a testament to the power of the human intellect to understand the laws of nature and to build machines that can extend our senses and our presence into the vast and beautiful wilderness of the cosmos. The quest to build a fusion engine, whether for a terrestrial power plant or a deep space starship, is fundamentally a quest to find and to master the perfect fuel. The ideal fusion fuel would be one that is abundant, easy to handle, and that fuses at the lowest possible temperature, releasing the maximum amount of energy. The universe's most abundant element, hydrogen, is the natural starting point. But the fusion of two ordinary hydrogen nuclei, the proton-proton chain that powers our sun, is an incredibly slow and inefficient process, far too slow to be practical for a man-made reactor. And so, fusion research has focused on the heavier isotopes of hydrogen deuterium and tritium. The deuterium-tritium DT reaction is, by a significant margin, the easiest fusion reaction to achieve. It has the lowest ignition temperature, around 100 million degrees Celsius, and the highest reaction rate at that temperature. In the DT reaction, a deuterium nucleus, 1 proton. 1 neutron fuses with a tritium nucleus, 1 proton. 2 neutrons to produce a helium nucleus. 2 protons, 2 neutrons, and a single high-energy neutron. This reaction releases a substantial amount of energy, about 17.6 million electron volts. The DT fuel cycle is the basis for almost all current. Mainstream fusion research, including the massive ITER project. The fuel itself is relatively abundant. Deuterium can be easily and cheaply extracted from ordinary seawater. About 1 in every 6,400 hydrogen atoms in the ocean is deuterium. Tritium, however, is a radioactive isotope with a short half-life of about 12 years, and it does not occur naturally in any significant quantity. And so, a practical DT fusion power plant must breed its own tritium. This is typically done by surrounding the fusion reactor with a blanket containing the light metal lithium. When the high-energy neutrons from the fusion reaction strike the lithium nuclei, they trigger a nuclear reaction that produces helium and tritium. The lithium itself is an abundant and widely available resource. So, in a sense, a DT fusion reactor is a device that burns the deuterium and lithium to produce helium and energy. While the DT fuel cycle is the most technologically accessible, it is not without its drawbacks. The high-energy neutrons produced in the reaction are a major engineering challenge. They bombard the walls of the reactor, causing the materials to become radioactive and to degrade over time. This process of neutron activation means that a DT fusion reactor will still produce a significant amount of low-level and intermediate-level radioactive waste. Although it is much less long-lived and problematic than the waste from a fission reactor. This has led to a search for advanced or aneutron fusion fuels, reactions that produce most of their energy in the form of charged particles rather than neutrons. The most promising of these is the deuterium-helium-3 DHE3 reaction. Helium-3 is a light, stable isotope of helium, and its fusion with deuterium produces a normal helium nucleus and a high-energy proton. This is a much cleaner reaction than DT, as it produces far fewer neutrons. The problem is that helium-3 is incredibly rare on Earth. It is, however, thought to be relatively abundant in the lunar regolith, the soil of the moon, where it has been deposited by the solar wind over billions of years. This has led to the tantalizing, if futuristic, prospect of mining the moon for helium-3 to fuel a future generation of clean fusion reactors on Earth, another, even more advanced. Neutronic fuel is the proton-boron PB11 reaction. This reaction fuses a proton with a boron-11 nucleus to produce 3 helium nuclei. It produces no neutrons at all, making it the cleanest of all possible fusion reactions. But it is also, by far, the most difficult to achieve, requiring temperatures that are at least 10 times higher than for DT fusion. The choice of fusion fuel is a complex trade-off between the ease of ignition, the energy output, the availability of the fuel, and the engineering challenges associated with the reaction products. For the first generation of fusion power plants, and likely for the first generation of fusion rockets, the deuterium-tritium fuel cycle will be the workhorse. But as our technology advances, as our ability to confine and to heat a plasma improves, we may one day be able to unlock the cleaner, more elegant, and ultimately more sustainable promise of the advanced neutronic fusion fuels. The challenge of creating a controlled, self-sustaining fusion reaction is one of the most difficult engineering problems ever conceived. It is the problem of building a piece of a star on Earth, of taming a substance that is 100 times hotter than the core of the Sun. As we have seen, the two primary approaches to this challenge, magnetic confinement and inertial confinement, are based on fundamentally different physical principles and engineering philosophies. Magnetic confinement is a strategy of patience. Its goal is to create a stable, steady-state plasma, holding it in a magnetic cage for long periods of time, allowing the fusion reactions to occur continuously. The most successful and widely studied magnetic confinement device is the tokamak, the donut-shaped machine that is the basis for the giant ITER experiment. A tokamak uses a powerful combination of magnetic fields to confine the plasma. A strong toroidal field, running the long way around the donut, is generated by a series of large, D-shaped superconducting magnets. This is the primary confining field. But this field alone is not enough. The charged particles of the plasma would quickly drift outwards and hit the walls. To create a stable, helical magnetic field structure that can confine the particles, a second, poloidal field is needed. This is generated by driving a massive electrical current on the order of millions of amps through the plasma itself. This plasma current is induced by a large transformer, with the plasma acting as the secondary coil. This combination of toroidal and poloidal fields creates a set of nested, twisted magnetic surfaces that trap the plasma particles. The tokamak is a clever and effective design, but it has its challenges. The need to drive a large current through the plasma makes it a pulsed device, and sustaining that current for long periods of time is a major engineering hurdle. The plasma is also prone to a host of complex instabilities and turbulent eddies that can cause a sudden loss of confinement, an event known as a disruption, an alternative, and in many ways more elegant. Magnetic confinement concept is the stellarator. Like a tokamak, a stellarator uses magnetic fields to confine a donut-shaped plasma. But instead of inducing a current in the plasma to create the necessary twisted field, a stellarator generates the entire magnetic field structure using a set of incredibly complex, twisted, and non-planar external magnetic coils. This is an engineering nightmare, but it has a major advantage because there is no need for a plasma current. A stellarator can, in principle, operate in a truly steady-state, continuous mode. And its complex three-dimensional magnetic field structure can be optimized to be much more stable and less prone to disruptions than a tokamak. For a long time, the difficulty of designing and building the complex coils of a stellarator meant that it lagged behind the tokamak in performance. But with the advent of powerful supercomputers for magnetic field design and advanced 3D printing-like manufacturing techniques for building the coils, the stellarator is now experiencing a major renaissance with new, sophisticated experiments like the Wendelstein 7X in Germany, beginning to challenge the dominance of the tokamak. Inertial confinement, on the other hand, is a strategy of brute force. Its goal is not to hold the plasma in a steady state, but to create the conditions for fusion in a brief, fleeting, and incredibly violent instant. At the National Ignition Facility, a tiny, spherical pellet of deuterium and tritium, just a few millimeters in diameter, is suspended in the center of a large target chamber. 192 of the world's most powerful laser beams are fired into the chamber, not at the pellet itself, but at the inner walls of a small gold cylinder called a hohlraum that surrounds the pellet. The laser energy is converted into a bath of soft X-rays inside the hohlraum, and it is this smooth, uniform bath of X-rays that ablates the outer surface of the fuel pellet, driving the implosion. This indirect drive approach is designed to create a very symmetric compression, which is crucial for achieving high densities and temperatures. The goal is to compress the fuel to a density of about 100 times that of solid lead, and to heat a small hotspot at its center to a temperature of over 100 million degrees, triggering a burn wave of fusion reactions that propagates outwards and consumes the surrounding dense fuel. The challenge of inertial confinement is one of incredible precision. The fuel pellet must be perfectly spherical. The laser beams must be perfectly timed and perfectly aimed. Any small asymmetry can ruin the implosion and prevent ignition. The debate between magnetic and inertial confinement, between the patient tortoise and the violent hare, has been one of the central themes of fusion research for decades. It is still not clear which approach, if any, will ultimately lead to a practical commercial fusion power plant. But the knowledge we are gaining from both is invaluable, and it is pushing the boundaries of our understanding of plasma physics, of material science, and of our ability to engineer and to control the very forces that shape the cosmos. The journey from a laboratory-based fusion experiment to a flight-ready, space-rated fusion propulsion system is a monumental one, a leap in technological complexity that will require a host of groundbreaking innovations. It is not simply a matter of shrinking a device like ITER and putting it on a rocket. A fusion engine for a spacecraft will have a very different set of design constraints and operational requirements than a terrestrial power plant. First and foremost, a fusion engine must be incredibly lightweight and compact. A device like ITER, with its thousands of tons of superconducting magnets and its massive concrete bioshield, is clearly not going to fly. A fusion rocket will require a revolution in magnet technology, a move towards new, high-temperature, superconducting materials that can generate incredibly strong magnetic fields in a much smaller and lighter package. These high-field magnets are the key to building a compact fusion reactor, as the fusion power density scales with the fourth power of the magnetic field strength. Doubling the field strength means you can get the same power out of a reactor that is 16 times smaller. This is a major focus of research at places like MIT's Plasma Science and Fusion Center and at several private fusion startups. Secondly, a fusion engine must be incredibly efficient, not just in terms of its fuel consumption, but in terms of its power-to-weight ratio. It must produce a huge amount of thrust for every kilogram of its own mass. This requires a very different design philosophy than a power plant, which is optimized for steady-state electricity generation. A fusion rocket will need a way to efficiently convert the energy from the fusion reaction into a directed, high-velocity jet of plasma. In a deuterium-tritium reactor, 80% of the energy is released in the form of high-energy neutrons. In a terrestrial power plant, these neutrons are absorbed in a blanket to produce heat, which is then used to drive a conventional steam turbine. But for a rocket, a more direct method of generating thrust is needed. Some concepts envision using the neutron energy to heat a propellant, like liquid hydrogen, in a nuclear thermal-like configuration. But a more elegant and ultimately more efficient approach is to use an aneutron fuel, like deuterium helium-3, where most of the energy is released in the form of charged particles. These charged particles can then be directed and accelerated by a magnetic nozzle, a kind of magnetic rocket engine, which would be far more efficient than a thermal system. This leads to the third major challenge, the need for advanced aneutronic fusion fuels. As we have seen, these fuels are much more difficult to ignite than deuterium-tritium, requiring higher temperatures and better plasma confinement. The development of a practical, compact, aneutronic fusion reactor is one of the greatest long-term challenges in the field. Fourth, a fusion engine must be incredibly robust and reliable. A spacecraft on a multi-year mission to the outer solar system cannot be brought into a dry dock for repairs. It must operate autonomously and reliably for decades in the harsh, unforgiving environment of deep space, with its extreme temperatures, its vacuum, and its constant bombardment of cosmic radiation. This requires a new level of engineering, of fault-tolerant design, of advanced robotics and artificial intelligence for autonomous operation and maintenance. Finally, there is the challenge of in-situ resource utilization. The ultimate dream of fusion propulsion is to be able to refuel the spacecraft from the resources that are available in space. This would require the development of technologies for mining the lunar regolith for helium-3, or for extracting deuterium from the water ice on Mars or the atmospheres of the gas giants. This is a long-term, multi-generational vision, but it is the vision that could truly untether humanity from its home planet. The path to fusion propulsion is a steep and difficult one. It will require not just incremental improvements, but a series of fundamental breakthroughs in plasma physics, in materials science, in magnet technology, and in systems engineering. But it is a path that we are now, for the first time, beginning to walk with a real sense of optimism and purpose. The landscape of space exploration is currently in the midst of a profound and exciting transformation, a new golden age driven by a convergence of new technologies, new scientific questions, and a new influx of commercial and international players. At the heart of this transformation is the James Webb Space Telescope, a revolutionary instrument that is opening up the infrared universe with a clarity and a sensitivity that is rewriting our textbooks on a monthly basis. Webb is allowing us to peer back in time to the cosmic dawn, to search for the light of the very first stars and galaxies that formed after the Big Bang. It is giving us the ability to analyze the atmospheres of Earth-sized exoplanets, to search for the chemical fingerprints of water, of methane, of oxygen, the potential biosignatures that could provide the first tantalizing evidence of life beyond our own world. It is a tool that is not just answering old questions, but is revealing new ones that we did not even know how to ask. In the realm of planetary science, we are in an era of unprecedented exploration of our own solar system. On Mars, the Perseverance rover is not just searching for signs of ancient microbial life in the rocks of an ancient river delta. It is also collecting the first-ever samples of the Martian surface that will be returned to Earth by a future mission, a complex international collaboration that will allow us to study the red planet in our own laboratories with a level of detail that is impossible with a robotic mission alone. And it is accompanied by Ingenuity, a tiny autonomous helicopter that has proven that powered, controlled flight is possible in the thin Martian atmosphere, opening up a new dimension for the future exploration of other worlds. Further out, a new wave of missions is being planned to the mysterious ocean worlds of the outer solar system. NASA's Europa Clipper, scheduled to launch in the mid-2020s, will perform a series of close flybys of Jupiter's icy moon Europa, using a suite of instruments to characterize its subsurface ocean and to search for plumes of water erupting from its surface, which could be sampled directly by a future lander. The Dragonfly mission will send a nuclear-powered quadcopter drone to Saturn's giant moon Titan, a world with a thick, nitrogen-rich atmosphere and rivers and lakes of liquid methane. Dragonfly will fly from location to location on Titan's surface, studying its complex organic chemistry and its potential for a form of life that is very different from our own. The commercialization of space is another major driver of this new era. Companies like SpaceX, with its reusable Falcon 9 and Starship rockets, are dramatically lowering the cost of access to space, making possible a new generation of ambitious scientific missions, of large-scale satellite constellations for global internet access, and, in the long term, of a self-sustaining human presence on the Moon and Mars. The renewed focus on a return to the Moon through NASA's Artemis program and the efforts of other international and commercial partners is not just about flags and footprints. It is about learning to live and to work off-world, to utilize the resources of the Moon, like its water ice and its potential reserves of helium-3, to build a sustainable and permanent human presence that can serve as a stepping stone for the much longer and more challenging journey to Mars and beyond. And in the background of all this activity, the quiet, patient work of fundamental research continues. The search for the nature of dark matter and dark energy, the quest for a theory of quantum gravity, the ongoing revolution in our understanding of fusion energy, these are the deep, theoretical underpinnings that will enable the next great leaps in our exploration of the cosmos. We are living in a remarkable and privileged time, a moment when the dreams of generations of scientists and explorers are beginning to come within our grasp. The challenges are still immense, the distances are still vast, and the universe is still full of mysteries. But for the first time in our history, we have the tools, the knowledge, and the global collaborative spirit to begin to answer the most profound questions of our existence, and to take our first, tentative steps into our future as a multiplanetary species. The field of nuclear fusion, once the domain of a few large, government-funded laboratories, is now experiencing a vibrant and disruptive renaissance, driven by a new wave of private companies and innovative, alternative approaches. This new space equivalent for fusion energy is accelerating the pace of progress and creating a healthy and diverse ecosystem of research and development. One of the most significant recent breakthroughs has come from the mainstream, but it is a breakthrough that has energized the entire field. In December of 2022 and again in 2023, the National Ignition Facility, NIF, at Lawrence Livermore National Laboratory in California announced that it had achieved ignition in an inertial confinement fusion experiment. For the first time in history, a fusion reaction in a laboratory had produced more energy than was delivered to the fuel target by the lasers. This was a monumental scientific achievement, a proof of principle that had been sought for over half a century. While NIF is not a design for a practical power plant, it is a massive, complex, and inefficient facility that can only perform a few shots per day. Its success has provided a powerful validation of the fundamental physics of fusion and has sent a wave of optimism and renewed investment through the entire fusion community. In the private sector, a number of well-funded and ambitious startups are challenging the long-held dominance of the tokamak and are pursuing a wide range of innovative fusion concepts. Companies like Helion Energy and TAE Technologies are two of the most prominent players in this new landscape. Helion is developing a unique, compact, and pulsed fusion device that uses a field-reversed configuration, a self-contained, stable plasma structure that is accelerated and compressed to fusion conditions. Their approach aims to directly convert the energy of the fusion products into electricity, bypassing the need for a complex and inefficient steam turbine, and they are using the clean, aneutron deuterium helium-3 fuel cycle. TAE Technologies is also pursuing an aneutron approach, using the proton-boron fuel cycle in a large linear device that collides two beams of plasma. Their focus is on achieving a stable, long-lived plasma, and they have made remarkable progress in understanding and controlling the complex physics of their field-reversed configuration. Another exciting area of innovation is in the development of high-temperature superconducting magnets. Commonwealth Fusion Systems, a spin-off from MIT, has successfully developed and tested a powerful, compact magnet using a new class of superconducting material. This magnet can generate a field strength that is far beyond what is possible with conventional superconductors, and it is the key technology behind their plan to build a compact, high-field, and net energy-producing tokamak called SPARC. This compact tokamak approach could offer a faster and cheaper path to commercial fusion energy than the massive decade-spanning projects like ITER. The advancements are not just in the hardware. Our understanding of plasma physics is being revolutionized by the power of supercomputing and artificial intelligence. Scientists are now using sophisticated machine learning algorithms to analyze the vast amounts of data from fusion experiments, to predict and to control plasma instabilities in real time, and to optimize the design of new fusion reactors. This synergy between experimental progress, theoretical understanding, and advanced computation is creating a powerful, positive feedback loop that is accelerating the entire field. The quest for practical fusion energy is still one of the greatest scientific and engineering challenges of our time, and the road ahead is still long and uncertain. But for the first time in a long time, there is a real, palpable sense that we are on the verge of a breakthrough. The combination of steady progress in the large international projects and a new dynamic ecosystem of private innovation is creating a powerful and exciting momentum. The dream of a world powered by the clean, safe, and abundant energy of the stars is no longer just a distant science fiction fantasy. It is a tangible and achievable goal, a goal that is now, finally, coming within our reach. The quest to harness the power of fusion is a global one, a grand collaborative endeavor that transcends national borders and political divides. It is a testament to the power of science to unite humanity in the pursuit of a common and noble goal. While the United States and the former Soviet Union were the early pioneers in fusion research, today, the field is a truly international one, with major research programs and experiments in Europe, in Asia, and around the world. At the forefront of this global effort is NASA. While its primary mission is space exploration, NASA has a long and deep interest in advanced propulsion, and it has maintained a small but influential research program in fusion propulsion concepts for decades. Through its innovative Advanced Concepts NIAC program, it has funded a number of early-stage speculative studies of novel fusion engine designs, from compact, pulsed systems to more exotic, magnetically nozzled concepts. NASA's role is not just to build the hardware, but to identify the key technological challenges and to foster the basic fundamental research that will be needed to one day make fusion propulsion a reality. On the academic front, a number of universities are major hubs of fusion research. The Princeton Plasma Physics Laboratory, PPPL, a U.S. Department of Energy national laboratory affiliated with Princeton University, has been a world leader in magnetic confinement fusion research for over 70 years. It was the home of the groundbreaking TFTR tokamak in the 1990s, and it continues to be a center of excellence in plasma physics, with a focus on both the fundamental science of fusion and the development of new, innovative reactor concepts, including the direct fusion drive. The Massachusetts Institute of Technology, MIT, is another major player. With its Plasma Science and Fusion Center, MIT has a long and distinguished history in the development of high-field, compact tokamaks and its recent work on high-temperature superconducting magnets, in collaboration with its spin-off company, Commonwealth Fusion Systems, is one of the most exciting and promising developments in the entire field. On the international stage, the European fusion community, coordinated through an organization called Eurofusion, is a powerful and integrated force. It operates the Joint European Tourist Jet in the UK, which is currently the world's largest and most powerful operating tokamak, and it is a major partner in the ITER project. In Asia, Japan, China, and South Korea all have advanced and ambitious fusion research programs, with a number of large, state-of-the-art tokamak and stellarator experiments. The Chinese East Tokamak, for example, has set a number of world records for long-pulse, high-temperature plasma operation, a crucial step towards steady-state fusion power. And in the background of all this applied research, there are the great fundamental physics laboratories, like CERN in Europe, the home of the Large Hadron Collider. While CERN's primary mission is to study the fundamental particles and forces of nature, its work has a deep and important synergy with fusion research. The technologies developed for particle accelerators, like large-scale superconducting magnets, advanced vacuum systems, and sophisticated particle detectors are often directly applicable to fusion devices. And the deeper our understanding of the fundamental laws of nature becomes, the better equipped we will be to understand and to control the complex physics of a fusion plasma. The global fusion community is a complex and interconnected ecosystem, a network of national laboratories, of universities, of international collaborations, and now of private companies. It is a community that is bound together by a shared and incredibly difficult challenge, a challenge that is so great that no single nation or institution can hope to solve it alone. It is a beautiful example of science at its best, a model for the kind of global collaboration we will need to solve the other great challenges of the 21st century. The experimental fusion reactors that are being built and operated around the world today are not just prototypes for future power plants. They are also invaluable tools for advancing our understanding of the fundamental physics that will be required to build a fusion propulsion system. They are the crucibles in which we are forging the knowledge and the technology for our future in space. At the most basic level, these experiments are teaching us how to control a substance that is inherently difficult to control, a high-temperature plasma. The physics of a fusion plasma is incredibly complex, a turbulent, chaotic dance of charged particles, of electric and magnetic fields, of waves and instabilities. Understanding and predicting this behavior is a grand challenge for modern physics. The vast amounts of data generated by these experiments, from a host of sophisticated diagnostic instruments that can measure the plasma's temperature, density, and magnetic field with incredible precision, are allowing us to test and to refine our theoretical models and our large-scale computer simulations. This fundamental understanding of plasma physics is absolutely essential for designing a fusion rocket. A propulsion system will need to operate with an even greater degree of stability and reliability than a terrestrial power plant, and it will need to do so in a much more compact and lightweight package. The lessons we are learning from experiments like ITER and JET about how to control plasma instabilities, how to heat the plasma efficiently, and how to manage the interaction between the plasma and the surrounding materials, are all directly applicable to the challenges of fusion propulsion. The development of materials is another crucial area where these experiments are paving the way. The inner walls of a fusion reactor are subjected to one of the most hostile environments imaginable, a constant bombardment of high-energy neutrons, of energetic plasma particles, and of intense heat. Developing materials that can withstand these conditions for long periods of time without degrading or becoming overly radioactive is a major focus of fusion research. This material science is directly relevant to the design of a fusion rocket, which will face similar, and in some ways even more extreme, conditions. The knowledge we are gaining about advanced radiation-resistant alloys, about tungsten and other high-temperature materials, and about novel liquid metal concepts for the reactor's first wall will all be essential for building a durable and long-lasting fusion engine. The experimental reactors are also a test bed for the development of crucial enabling technologies like superconducting magnets, powerful heating systems, and robotic maintenance systems. The large, high-field superconducting magnets being built for ITER, for example, are a major technological leap, and the experience we are gaining in designing, building, and operating these massive and complex systems will be invaluable for the future development of the more compact, higher-field magnets that will be needed for a fusion rocket. In a very real sense, the experimental fusion reactors of today are the precursors, the ancestors, of the fusion engines of tomorrow. They are the places where we are learning the fundamental language of the stars, a language that we must master before we can hope to build a ship that can sail between them. The journey from a terrestrial experiment to a space-based propulsion system is a long one, but it is a journey where each step on Earth brings us a little bit closer to the dream of a future among the stars. The promise of nuclear fusion propulsion is not just about incremental improvements in our current capabilities. It is about a fundamental, paradigm-shifting leap in what is possible in space exploration. The advantages of fusion over traditional chemical propulsion are so profound that they would open up a completely new era of human and robotic exploration of the cosmos. The most significant of these advantages is the immense gain in specific impulse, the primary measure of a rocket engine's efficiency. A chemical rocket works by burning a fuel and an oxidizer to create a hot gas, which is then expelled through a nozzle. The efficiency of this process is limited by the chemical energy stored in the bonds of the propellant molecules. The best chemical rockets, like the liquid hydrogen/liquid oxygen engines of the space shuttle, have a specific impulse of about 450 seconds. A fusion rocket, on the other hand, is not limited by chemical energy. It is powered by the much more potent energy of the atomic nucleus. The exhaust velocity of the plasma from a fusion engine would be orders of magnitude higher than that of a chemical rocket, leading to a specific impulse that could be in the range of 10,000 to 1 million seconds. This is a game-changing difference. The rocket equation tells us that the final velocity of a spacecraft is proportional to its exhaust velocity. This means that a fusion rocket could achieve much higher speeds with a much smaller amount of fuel. The journey to Mars, which currently takes 6 to 9 months with a chemical rocket using a minimum energy Hohmann transfer orbit, could be reduced to just a few weeks with a high-performance fusion engine. This is not just about saving time, it is about saving lives. A shorter transit time would dramatically reduce the crew's exposure to the two great dangers of interplanetary space: the constant, low-level galactic cosmic radiation, and the debilitating long-term effects of microgravity on the human body. Another profound advantage is the potential for continuous, high-thrust operation. A chemical rocket can only fire for a few minutes at a time before its fuel is exhausted. A spacecraft on a journey to Mars spends most of its time coasting passively through space. A fusion rocket, with its high power density and its incredibly efficient fuel, could, in principle, provide a continuous thrust for the entire journey. It could accelerate for the first half of the trip and then turn around and decelerate for the second half. This constant thrust trajectory is not only much faster than a coasting trajectory, But it also has another remarkable benefit: it could provide a continuous artificial gravity for the crew. By maintaining a constant acceleration of 1g, the same as the gravity on the surface of the Earth, a fusion-powered spacecraft could simulate a normal terrestrial environment for the entire journey. This would completely eliminate the health problems associated with microgravity, and it would make the experience of long-duration spaceflight far more comfortable and sustainable. Furthermore, the immense power output of a fusion reactor would not just be for propulsion. It would also provide a copious amount of electricity to power the spacecraft's systems, its life support, its scientific instruments, its communications. A fusion-powered spacecraft would not be a power-starved, minimalist vessel, but a true mobile outpost, a small city in space with all the energy it needs to support a thriving human presence. The combination of high speed, continuous thrust, artificial gravity, and abundant power is what makes fusion propulsion a truly transformative technology. It is the technology that could take us from a species that makes brief, timid forays into our own cosmic backyard into a true, multiplanetary species, with permanent, self-sustaining settlements on the Moon, on Mars, and perhaps one day in the vast and beautiful wilderness of the outer solar system. The difference in the energy output between a chemical reaction and a nuclear fusion reaction is a direct consequence of the difference in the forces that are at play. Chemical reactions, like the burning of a rocket fuel, are all about rearranging the electrons in the outer shells of atoms. These reactions involve the breaking and forming of chemical bonds, which are governed by the electromagnetic force. The energy released in a chemical reaction is a measure of the difference in the electromagnetic potential energy between the reactants and the products. And while this energy can be substantial enough to lift a multi-ton rocket off the ground, it is a tiny fraction of the total mass energy of the fuel, as described by Einstein's E=mc². The energy density of the best chemical rocket fuel, liquid hydrogen and liquid oxygen, is about 13.4 megajoules per kilogram. Nuclear reactions, on the other hand, are all about rearranging the protons and neutrons within the nucleus of an atom. These reactions involve the strong nuclear force, the most powerful of the four fundamental forces of nature. The strong force is about 100 times stronger than the electromagnetic force, but it only operates over the incredibly short distances found within the atomic nucleus. The energy released in a nuclear reaction is a measure of the difference in the nuclear binding energy between the initial and final nuclei. And because the strong force is so much more powerful than the electromagnetic force, the energy released in a nuclear reaction is millions of times greater than the energy released in a chemical reaction of the same mass. A single deuterium-tritium fusion reaction, for example, releases about 17.6 million electron volts of energy. To put this in perspective, the energy density of DT fusion fuel is about 337 million megajoules per kilogram. This is about 25 million times greater than the energy density of chemical rocket fuel. This is the source of fusion's immense power. It is tapping into the much stronger and much more potent energy source of the strong nuclear force. This enormous difference in energy density is what makes fusion propulsion so revolutionary. A chemical rocket is fundamentally limited by the amount of energy it can get out of each kilogram of propellant. A fusion rocket, by tapping into the power of the nucleus, can be millions of times more efficient. This means it can achieve much higher exhaust velocities, which, according to the rocket equation, translates directly into much higher final speeds for the spacecraft. It also means that a fusion rocket needs to carry far less fuel for a given mission, which dramatically improves the mass fraction, the ratio of the payload mass to the total initial mass of the rocket. This is why fusion is seen as the key to unlocking the solar system. It is not just a slightly better engine. It is a fundamentally different kind of engine, one that operates on a different and far more powerful physical principle. The difference between a chemical rocket and a fusion rocket is, in many ways, the difference between the age of sail and the age of steam, or the age of the propeller and the age of the jet. It is a quantum leap in our ability to travel, a leap that will open up new frontiers and new possibilities that are currently beyond our wildest dreams. The impact of fusion propulsion on our exploration of the solar system would be nothing short of revolutionary. It would transform the planets and moons of our cosmic neighborhood from distant, exotic destinations, reachable only by long, arduous, and infrequent robotic missions, into a new, accessible frontier for human exploration, for science, and for settlement. The journey to Mars, our closest and most Earth-like neighbor, would be the first and most obvious beneficiary. With current chemical propulsion, a round-trip human mission to Mars is a daunting, multi-year undertaking. The long 6 to 9 month transit time in each direction, combined with a stay of over a year on the Martian surface waiting for the correct planetary alignment for the return journey, would expose the crew to a significant and potentially life-threatening dose of cosmic radiation and the debilitating effects of prolonged microgravity. A high-performance fusion rocket could cut the transit time to Mars to just a few weeks. This would not just make the journey safer and more comfortable, it would fundamentally change the logistics and the economics of Mars exploration. A fast transit would allow for a sprint mission architecture where a crew could travel to Mars, spend a few weeks or months on the surface, and return to Earth, all within the span of a single year. This would dramatically reduce the total mission duration, the amount of supplies needed, and the overall complexity and risk. It would make a human presence on Mars not a once-in-a-generation, Apollo-style endeavor, but a routine and sustainable enterprise. But the true promise of fusion extends far beyond Mars. The outer solar system, the realm of the gas giants and their incredible retinues of icy moons, is currently the domain of patient, multi-decade robotic explorers. The Voyager missions, launched in the 1970s, took over a decade to reach Neptune. A human mission to these distant worlds with chemical rockets is simply not feasible. But a fusion-powered spacecraft, with its high speed and continuous thrust, could make the journey to Jupiter in a matter of months and to Saturn in less than a year. This would open up the ocean worlds of the outer solar system moons like Europa, Enceladus, and Titan, which are thought to harbor vast, subsurface oceans of liquid water to a new era of exploration and perhaps, one day, of human presence. Imagine a permanent, fusion-powered research station in orbit around Jupiter, serving as a base for robotic submarines exploring the dark, mysterious ocean of Europa, searching for signs of life. Imagine a human outpost on the surface of Titan, a world with a thick atmosphere and lakes of liquid methane, a world that is a natural laboratory for studying the kind of prebiotic chemistry that may have led to life on the early Earth. These are the kinds of missions that fusion propulsion would make possible. It would also revolutionize our ability to explore the smaller, more primitive bodies of the solar system, the asteroids and the comets. A fusion-powered spacecraft would have the performance to rendezvous with, to orbit, and to land on these objects, to mine their resources, and to return samples to Earth. The asteroids are rich in valuable metals and water ice, resources that could be used to fuel a future in-space economy. And the comets are pristine, frozen relics from the very beginning of the solar system. Time capsules that hold the secrets to our own origins. Fusion propulsion would give us the key to unlock these cosmic treasure chests. In the broadest sense, fusion propulsion would transform our solar system from a series of isolated, distant points of light into a true interconnected neighborhood. It would allow us to build a robust and sustainable infrastructure of transportation, of communication, of human presence, that spans the entire system, from the sun-baked plains of Mercury to the icy shores of the Kuiper Belt. It is the technology that could finally fulfill the dream of a truly spacefaring civilization. The challenges and limitations that confront our exploration of the cosmos are as vast as space itself. They are a sobering but also inspiring reminder of the immense scale of the universe and the fragility of our own human endeavor. The most fundamental of these is the tyranny of distance. The numbers are so large they are difficult to comprehend. Our solar system is a tiny island in the vast, empty ocean of the Milky Way galaxy, which is, in turn, just one of hundreds of billions of galaxies in the observable universe, the nearest star to our Sun. Proxima Centauri is over 4 light-years away. With our current, fastest spacecraft, a journey to this nearest stellar neighbor would take over 70,000 years. Interstellar travel, for now, remains a dream for a very distant future. Even within our own solar system, the distances are daunting. A journey to Mars, our closest planetary neighbor, is a multi-month odyssey. A journey to the outer planets is a multi-year, and in some cases, multi-decade, undertaking. These long travel times are not just a logistical challenge. They are a fundamental human challenge. They expose our astronauts to the relentless hazards of the deep space environment. Outside the protective bubble of Earth's magnetic field, our bodies are bombarded by a constant low-level rain of high-energy galactic cosmic rays. Particles that have been accelerated to near light speed by distant supernovae and other violent cosmic events. This radiation can damage our DNA, increasing the risk of cancer, and can also affect the central nervous system, leading to cognitive and behavioral problems. The long-term effects of this radiation on human health are still not fully understood, and developing effective, lightweight shielding is a major engineering challenge. The other great physiological challenge is the absence of gravity. In the weightless environment of space, our bodies begin to adapt in ways that are detrimental to our health. Our bones lose density, our muscles atrophy, our cardiovascular system deconditions, our immune system is suppressed, and our sense of balance is disrupted. These effects can be partially mitigated by a rigorous daily regime of exercise, but they remain a major concern for long-duration missions. And beyond the physical challenges, there are the profound psychological ones. The confinement, the isolation, the monotony of a multi-year journey in a small, enclosed space, cut off from the sights, the sounds, and the society of Earth, would place an immense strain on the mental health of any crew. The cost of space exploration is another major limitation. Building, launching, and operating a complex, robotic spacecraft, let alone a human mission, is an incredibly expensive undertaking, often running into the billions of dollars. This means that space science is often in competition with other, more immediate, terrestrial priorities for a limited pool of public funding. This forces difficult choices and often means that ambitious to high-risk, high-reward missions are postponed or canceled. The development of reusable rocket technology is beginning to change this economic equation. But deep space exploration will likely always be a costly and challenging enterprise. Finally, there are the technological limitations themselves. Our propulsion systems are still, in many ways, primitive. Our power systems are limited. Our ability to build robust, autonomous, and self-repairing systems that can operate for decades in the harsh environment of space is still in its infancy. And our life support systems, while remarkably effective, are still not fully closed loop, meaning we still rely on resupplying our crews with consumables from Earth. Each of these challenges of distance, of environment, of cost, of technology is a formidable one, but they are not insurmountable. They are the challenges that are driving a new wave of innovation, of creativity, of international collaboration. They are the mountains that we, as a species, are learning to climb, and in the process of climbing them, we are not just learning about the universe. We are learning about ourselves, about our own limits, about our own resilience, and about our own boundless potential. The development of a practical, flight-ready fusion engine is one of the most formidable and multifaceted engineering challenges ever conceived. It is a problem that pushes the boundaries of a dozen different scientific and technological disciplines simultaneously. At the very heart of the challenge is the problem of the plasma itself, creating a stable, high-temperature, high-density plasma and confining it for long enough for a significant number of fusion reactions to occur is the central, defining problem of fusion research. In a magnetic confinement device, this means developing sophisticated magnet systems, powerful heating techniques, and advanced feedback control algorithms to tame the turbulent, chaotic nature of the plasma. In an inertial confinement device, it means developing incredibly powerful and precise lasers or particle beams, and fabricating fuel pellets with a degree of perfection that is almost beyond belief. The second major challenge is one of materials science. The inner first wall of a fusion reactor is subjected to an environment of almost unimaginable hostility. It must withstand a constant bombardment of high-energy neutrons, which can cause the material to become brittle and radioactive. It must withstand a high heat flux from the plasma radiation, and it must be compatible with the plasma itself, meaning it should not erode too quickly or release impurities that could cool the plasma and quench the reaction. Finding a material, or a combination of materials, that can survive in this environment for the long operational lifetime of a spacecraft is a major ongoing area of research. Tungsten, with its high melting point, is a leading candidate, but new, advanced alloys and self-healing liquid metal concepts are also being explored. The third challenge is that of the fuel cycle. For a deuterium-tritium engine, this means developing a robust and efficient tritium breeding blanket, a component that surrounds the reactor and uses the neutrons from the fusion reaction to breed new tritium fuel from lithium. This is a complex nuclear chemical engineering problem. It also means developing systems for safely handling and recycling the radioactive tritium fuel within the closed environment of a spacecraft. The fourth challenge is that of energy extraction and conversion. The energy from the fusion reaction is released in the form of high-energy particles, mostly neutrons and helium nuclei. This energy must be captured and efficiently converted into both electricity to power the spacecraft and directed thrust for propulsion. This requires the development of advanced thermal management systems, of high-efficiency heat exchangers and power conversion cycles, and of novel magnetic nozzle designs that can direct the flow of the hot plasma to generate thrust. The fifth challenge is one of systems integration. A fusion engine is not a standalone component. It is part of a larger, incredibly complex system, the spacecraft itself. The engine must be integrated with the power systems, the thermal control systems, the guidance and navigation systems, and the life support systems. The weight, the size, and the power requirements of the fusion engine must all be balanced against the other requirements of the mission. This is a monumental systems engineering challenge, one that requires a holistic and interdisciplinary approach. Finally, there is the challenge of safety and reliability. A fusion engine for a human-rated spacecraft must be designed to an unprecedented level of safety. It must have multiple, redundant safety systems, robust containment structures, and fail-safe mechanisms to ensure that, in the event of any malfunction, the crew and the spacecraft are protected. And it must be able to operate reliably and autonomously for many years, far from any possibility of repair or maintenance. Each of these challenges is a grand challenge in its own right, and they must all be solved, and solved together, for the dream of fusion propulsion to become a reality. It is a quest that will likely take decades of dedicated, focused, and well-funded research and development. But it is a quest that is driven by a vision that is worthy of the effort, a vision of a future where humanity is no longer confined to its cradle, but is free to explore the vast and wonderful expanse of the solar system and beyond. The question of safety is a paramount and non-negotiable one in all aspects of space exploration, and it takes on a particularly sharp focus when we consider the use of nuclear technology. The history of the atomic age on Earth has been a complex and often fraught one, a story that includes not just the promise of clean energy, but also the terror of nuclear weapons and the specter of catastrophic accidents. And so, it is natural and necessary that the prospect of using nuclear reactions to power our spacecraft should be met with a high degree of scrutiny and a profound sense of responsibility. It is important, however, to distinguish between the safety considerations of nuclear fission and nuclear fusion. A nuclear fission reactor, like those used in today's power plants and in some military submarines and icebreakers, works by creating a controlled, self-sustaining chain reaction in a core of heavy radioactive elements like uranium. The primary safety concern in a fission reactor is the potential for this chain reaction to go out of control, leading to a meltdown of the reactor core and the release of a large amount of highly radioactive fission products into the environment. This is what happened in the accidents at Chernobyl and Fukushima. A fission-powered spacecraft would have to be designed with multiple, redundant, and robust safety systems to prevent such an accident, particularly during the launch phase, where the risk of a catastrophic failure is highest. The waste from a fission reactor is also a major long-term safety concern. Nuclear fusion, on the other hand, is a fundamentally different and inherently safer process. A fusion reaction is not a chain reaction. It is a process that requires a very specific and extreme set of conditions. Temperatures of over 100 million degrees, a high-density plasma, and a powerful confinement system to be sustained. If any of these conditions are not met, if there is a breach of the vacuum, a failure of the magnets, or a disruption in the plasma, the fusion reaction simply stops. It is a fire that requires constant, active stoking to keep it burning. A runaway reaction or a meltdown in a fusion reactor is a physical impossibility. The fire simply goes out. The primary safety concern in a fusion reactor is not a catastrophic accident, but the management of the radioactive tritium fuel and the activation of the reactor structure by the high-energy neutrons produced in the deuterium-tritium reaction. Tritium is a radioactive isotope of hydrogen, but it is a low-energy beta emitter with a relatively short half-life of 12.3 years, which makes it far less hazardous than the long-lived waste products of a fission reactor. A fusion-powered spacecraft would, of course, need to have robust systems for safely handling and containing the tritium fuel. The neutron activation of the reactor's structural materials is a more significant long-term concern. Over time, the constant bombardment of neutrons will make the materials of the first wall and the breeding blanket radioactive. The goal of fusion materials research is to develop low-activation materials that will become less radioactive and whose radioactivity will decay much more quickly than the materials in a fission reactor. This would make the eventual decommissioning of a fusion engine a much simpler and safer process. The regulatory framework for the use of nuclear technology in space is a complex and evolving one. The Outer Space Treaty of 1967 prohibits the placing of nuclear weapons in orbit, but it allows for the use of nuclear power sources for peaceful purposes. There are established international guidelines and safety protocols for the use of radioisotope thermoelectric generators, RTGs, the small fission-based power sources that have been used safely and reliably on dozens of deep space missions. A similar, and even more rigorous, framework would need to be developed for the much more powerful nuclear reactors that would be used for propulsion. This will require a transparent and collaborative process, involving space agencies, regulatory bodies, and the public, to ensure that the immense benefits of nuclear propulsion are pursued in a way that is safe, responsible, and sustainable. The journey to fusion propulsion will be a long one, but it is a journey where safety must be the primary consideration at every single step of the way. The economic and societal implications of developing and deploying fusion propulsion technology are as profound and far-reaching as the scientific and technological ones. The journey to a fusion-powered future in space will require a sustained and significant investment of resources, a global commitment on the scale of the Apollo program or the construction of the International Space Station. The initial research and development costs are substantial, building the large, experimental facilities needed to advance the science of plasma physics, developing the new materials and technologies, and eventually, designing, building, and testing a flight-ready fusion engine is an enterprise that will likely run into the tens, and perhaps hundreds, of billions of dollars over the coming decades. This level of investment will require a strong and stable commitment from governments around the world, as well as an increasing involvement from the private sector. But while the upfront costs are high, the potential long-term returns are almost incalculable. A successful fusion propulsion system would not just be a new kind of rocket engine. It would be a new kind of economic engine, a technology that could unlock the vast resources and the immense potential of the solar system. The ability to travel quickly and efficiently to the Moon, to Mars, and to the asteroid belt would open up new frontiers for resource extraction. The Moon is rich in certain metals and, as we have seen, is a potential source of the advanced fusion fuel, helium-3. The asteroids are a treasure trove of platinum group metals, which are rare on Earth but essential for many of our advanced technologies, as well as vast quantities of water ice, which can be broken down into hydrogen and oxygen to provide breathable air, drinking water, and rocket propellant. A fusion-powered transportation infrastructure would be the key to building a true, self-sustaining, in-space economy. An economy where the resources of the solar system are used to support a growing human presence beyond the Earth. This would not just be about creating new industries and new wealth. It would be about ensuring the long-term survival and resilience of our species. A multiplanetary civilization, with self-sufficient outposts on the Moon and Mars, would be far less vulnerable to the existential risks that threaten a species confined to a single, fragile planet. From asteroid impacts and supervolcanoes to pandemics and nuclear war, the societal implications are equally profound. The quest for fusion, both for energy on Earth and for propulsion in space, is a powerful driver of scientific and technological innovation. The challenges of fusion are so great that they are pushing the boundaries in a host of different fields, from materials science and superconductivity to advanced computing and artificial intelligence. The breakthroughs we make on the path to fusion will have a ripple effect throughout our society, leading to new technologies and new industries that we cannot yet even imagine. And at a deeper cultural level, the journey to a fusion-powered future is a journey that can inspire and unite us. The image of a human-crewed starship, powered by its own miniature star, embarking on a journey to explore another world, is a powerful and archetypal one. It speaks to our deepest and noblest aspirations as a species, our desire to explore, to discover, to understand, and to reach for the heavens. It is a vision that can inspire a new generation of scientists, of engineers, of explorers. And it is a vision that can remind us of what we are capable of when we work together, when we set our sights on a grand and audacious goal, and when we have the courage and the persistence to pursue a dream that may take generations to fully realize. The economics of fusion are challenging, but the value of a future where humanity has a secure and inspiring destiny among the stars is, in the end, priceless. The design of a spacecraft is a complex and beautiful art, a delicate and high-stakes dance between the unforgiving laws of physics and the ambitious goals of a mission. And the design of a fusion-powered spacecraft will be a dance of unprecedented complexity, a complete rethinking of the fundamental architecture of a space vehicle. A chemical rocket is, in essence, A flying fuel tank. The vast majority of its mass is propellant, and the engine is a relatively small and simple component. A fusion-powered spacecraft would be the opposite. It would be a flying power plant. The fuel mass would be a tiny fraction of the total, while the engine, the fusion reactor itself, would be a large, complex, and massive system that would dominate the design of the entire vehicle. The overall architecture of a fusion spacecraft would be dictated by the need to manage the immense power and the unique products of the fusion reaction. The reactor would likely be placed at one end of a long, truss-like structure, with the crew habitat and the payload located at the far end to maximize the distance from the radiation source of the reactor and the magnetic nozzle. The space between would be occupied by the other essential subsystems. The thermal management system would be one of the most critical and visually striking features. A fusion reactor, even a highly efficient one, will generate a huge amount of waste heat that must be radiated away into space. This will require massive, lightweight radiators, perhaps unfolding like giant wings, with a surface area of thousands of square meters, glowing a dull red as they dissipate the excess heat into the cold, dark vacuum. The power management and distribution system would be the spacecraft's circulatory system, a network of superconducting cables and power converters that would take the electricity generated by the reactor and distribute it to the various subsystems, including the powerful magnets of the reactor itself and the scientific instruments of the payload. The propulsion system would be the heart of the design. In an anemotronic design, this would be a large, carefully shaped magnetic nozzle. A set of powerful magnetic coils that would take the hot, charged plasma from the reactor and direct it into a high-velocity jet, generating thrust. The design of this nozzle would be a complex exercise in magnetohydrodynamics, the science of electrically conducting fluids, as it would need to detach the plasma from the magnetic field lines without it hitting the structure of the nozzle itself. The fuel storage and processing system would also be a critical component. For a DT engine, this would include cryogenic tanks for the deuterium, a robust and shielded system for storing and handling the radioactive tritium, and the complex, nuclear chemical plant of the tritium breeding blanket. And, of course, there is the radiation shield, a significant amount of shielding. Likely a combination of lightweight materials like liquid hydrogen or water and denser materials like tungsten would be needed to protect the crew and the sensitive electronics from the neutrons and gamma rays produced by the fusion reaction. This shield would be one of the heaviest components of the spacecraft, and its design would be a delicate trade-off between safety and mass. The design of a fusion-powered spacecraft is a challenge that will require a new generation of engineers and a new way of thinking about how to build a machine that can operate at the very edge of what is technologically possible. It will be a machine that is part power plant, part laboratory, part home. A self-contained, artificial world designed to carry a small, fragile piece of humanity on a journey through the vast and beautiful wilderness of the solar system. It is a design challenge of epic proportions, but it is the challenge we must meet if we are to take the next great step in our cosmic journey. The development of advanced superconducting materials is one of the most critical and enabling technologies on the path to practical fusion propulsion. Superconductors are a remarkable and mysterious class of materials that, when cooled below a certain critical temperature, can conduct electricity with zero resistance. This means that a current, once started in a superconducting loop, will flow forever without any loss of energy. This property makes them the perfect material for building the powerful, high-field electromagnets that are needed to confine a fusion plasma. A conventional copper wire electromagnet is limited by the heat that is generated by the electrical resistance of the wire. If you try to drive too much current through it to create a very strong magnetic field, the wire will simply melt. A superconducting magnet, on the other hand, has no resistance. and so it can carry immense currents and generate incredibly powerful magnetic fields, far beyond what is possible with conventional magnets. This is absolutely essential for fusion. The effectiveness of magnetic confinement depends on the strength of the magnetic field. A stronger field can confine a denser plasma, which leads to a much higher fusion reaction rate. In fact, the fusion power output of a tokamak scales with the fourth power of the magnetic field strength. This means that if you can double the field strength, you can get 16 times more fusion power out of the same sized device. Or you can get the same amount of power out of a device that is 16 times smaller. This is the key to building a compact fusion reactor, the kind of small, powerful, and lightweight engine that would be needed for a spacecraft. For a long time, fusion research was limited to low-temperature superconductors, materials like niobium tin that need to be cooled with expensive and difficult-to-handle liquid helium to a temperature of just a few degrees above absolute zero. But in the 1980s, a new class of high-temperature superconducting materials was discovered, ceramic compounds that can superconduct at the much more manageable temperature of liquid nitrogen. These new materials have the potential to revolutionize the design of fusion reactors. They can operate at a higher temperature, which makes the cryogenic cooling system much simpler and more efficient. And they can also carry a much higher current density, which means they can be used to build even more powerful and more compact magnets. The development of these high-temperature superconductors into practical, robust, and manufacturable wires and tapes has been a long and difficult process. But in recent years, there have been major breakthroughs. Researchers at MIT and its spin-off company, Commonwealth Fusion Systems, have successfully built and tested a large-scale, high-field magnet using a new, high-temperature superconducting tape. This magnet achieved a field strength of 20 Tesla, the most powerful fusion magnet of its kind ever created. This is a game-changing technology. It is the technology that is enabling the construction of the Spark experiment, a compact, high-field tokamak that is designed to be the first fusion device in history to achieve a net energy gain in a machine that is a fraction of the size of ITER. And it is the technology that will be essential for building the compact, powerful, and lightweight magnets that will be needed for a fusion rocket engine. The synergy between superconductivity and fusion is a beautiful example of how progress in one area of science can enable a revolution in another. The quest to understand and to engineer these strange and wonderful quantum materials is not just a quest for more efficient power lines or faster maglev trains. It is a quest that is paving the way for us to build our own miniature stars and to one day use them to travel to other worlds. The process of testing and validating a new and revolutionary technology like fusion propulsion is a long, arduous, and incremental one. It is a journey that must be taken with a profound sense of caution, of rigor, and of respect for the immense power that we are seeking to unleash. The journey begins, as it always does, on the ground, in the realm of theory and computer simulation. Before any hardware is built, scientists and engineers must develop detailed, high-fidelity computer models that can simulate the complex physics of the fusion plasma, the behavior of the materials, and the integrated performance of the entire propulsion system. These simulations are run on some of the world's most powerful supercomputers, and they are an essential tool for exploring the vast design space, for identifying potential problems, and for optimizing the performance of the engine before a single piece of metal is cut. The next step is the construction of subscale, experimental components. This involves building and testing the individual parts of the engine. The magnets, the heating systems, the diagnostic instruments, the vacuum chamber in a laboratory environment. The goal here is to validate the design of each component, to test its performance against the predictions of the simulations, and to gain the practical and hands-on experience that is needed to build the full-scale system. This is a painstaking process of iteration, of trial and error, of learning from failures and celebrating small successes. Once the components have been validated, the next step is to build an integrated, ground-based test reactor. This would be a full-scale prototype of the fusion engine, designed to operate in a large vacuum chamber that can simulate the conditions of space. The primary goal of this ground-based testing would be to demonstrate the reliable and sustained operation of the entire engine system. It would involve a long and meticulous campaign of experiments to characterize the engine's performance across its full range of operating parameters: its thrust, its specific impulse, its efficiency, its thermal output. These tests would be heavily instrumented, with a vast array of sensors to monitor every aspect of the engine's health and performance. And they would be conducted with a rigorous attention to safety, with multiple redundant containment and shutdown systems to ensure that any off-normal event can be safely managed. Only after a long and successful campaign of ground-based testing, after the technology has been proven to be reliable, predictable, and safe, would we be ready for the final step of flight test in space. This would likely involve an unmanned robotic mission, a dedicated fusion flight demonstrator. This spacecraft would be designed to test the operation of the fusion engine in the true environment of space, with its vacuum, its microgravity, and its radiation. The mission would involve a series of carefully planned engine burns to demonstrate the engine's ability to provide a controlled, sustained thrust, to perform orbital maneuvers, and to operate autonomously for a long period of time. This first flight of a fusion engine would be a monumental milestone in the history of space exploration, a moment akin to the first flight of the Wright brothers or the first launch of a satellite. It would be the moment when the dream of fusion propulsion finally leaves the realm of science fiction and becomes a tangible, demonstrated reality. The path from the computer screen to the launch pad is a long and challenging one. But it is a path that must be walked, step by careful step, with a deep and abiding commitment to scientific rigor, to engineering excellence, and to the safety of all those who will one day entrust their lives to this new and revolutionary technology. A successful fusion propulsion system will be a machine that is not just powerful, but also elegant, efficient, and robust. It will be a system that has met a stringent and demanding set of criteria, a testament to our mastery of one of the most complex and challenging technologies ever conceived. The first and most fundamental criterion is, of course, a sustained net positive energy output. The engine must produce significantly more fusion power than is required to heat and to confine the plasma and to run all the other subsystems of the engine. This energy gain, or Q value, is the sine qua non of practical fusion. For a power plant, a Q value of at least 10 is considered necessary. For a propulsion system, where efficiency is paramount, the target will likely be even higher. The second criterion is a high specific power, or power-to-weight ratio. The engine must produce a large amount of thrust and electrical power for every kilogram of its own mass. This is the key to building a spacecraft that is not just a massive engine with a tiny payload, but an efficient and capable vehicle. This will require a design that is both incredibly powerful and incredibly lightweight, a challenge that will push the limits of materials science and magnet technology. The third criterion is a high specific impulse. As we have seen, this is a measure of the engine's fuel efficiency, and it is directly related to the exhaust velocity of the plasma. A fusion engine must be able to generate a very high exhaust velocity to enable the fast interplanetary transits that are its primary promise. The specific impulse will likely be a tunable parameter, allowing the engine to operate in a high-thrust, lower-efficiency mode for getting out of a planet's gravity well, and a low-thrust, higher-efficiency mode for cruising in deep space. The fourth criterion is reliability and longevity. A fusion engine for a human mission to Mars or the outer solar system must be able to operate continuously and reliably for months, and perhaps even years, with no possibility of external maintenance. This requires a level of robustness and fault tolerance that is far beyond that of any current propulsion system. It will require advanced AI-driven control systems that can monitor the health of the engine in real time and can autonomously diagnose and respond to any off-normal events. The fifth criterion is safety. The engine must be designed to be inherently safe, with multiple redundant systems to prevent any release of radioactive material, particularly the tritium fuel. The radiation shielding must be sufficient to protect the crew and the sensitive electronics from the neutrons and gamma rays produced by the fusion reaction, and it must do so without adding an excessive amount of mass to the spacecraft. And the sixth and final criterion is fuel sustainability. The ideal fusion engine would be one that can operate on a fuel that is either abundant and easy to handle, like deuterium and helium-3, or one that can be bred in situ, like tritium from lithium. The ultimate goal would be to develop an engine that can be refueled using the resources that are available in space, freeing humanity from its reliance on terrestrial resources and enabling a truly self-sustaining presence in the solar system. These are the 6 pillars of a successful fusion propulsion system. They are a daunting and ambitious set of requirements, a grand challenge that will require decades of dedicated research and innovation. But they are also a clear and compelling roadmap, a guide for the journey that will, if we are successful, take us from our home planet and out into the vast and beckoning frontier of the cosmos. The process of testing a fusion propulsion system will be a fundamentally different and far more complex undertaking than the testing of a traditional chemical rocket engine. A chemical rocket is, at its core, a controlled explosion. The testing process is primarily about ensuring that this explosion is stable, predictable, and that it produces the required amount of thrust without destroying the engine. A static fire test, where the engine is bolted to a massive test stand and fired for a few minutes, is the standard and effective way to validate its performance. A fusion engine, on the other hand, is not an explosion. It is a miniature, artificial star. The testing process is not just about measuring thrust. It is about creating, confining, and controlling a substance that is one of the most complex and unstable forms of matter in the universe. The test facilities for a fusion engine will not be simple concrete bunkers. They will be sophisticated, multi-billion-dollar scientific laboratories. The testing of a fusion engine will be a long, incremental, and data-rich process, a scientific campaign as much as an engineering validation. It will begin with the testing of individual components in specialized facilities, the superconducting magnets in large, cryogenic test stands, the plasma heating systems in dedicated vacuum chambers, the first-wall materials in facilities that can simulate the intense neutron and heat bombardment of a fusion environment. The next step will be the integration of these components into a subscale, experimental reactor. This will be a device that is not designed to produce a net energy gain, but to study the physics of the plasma in the specific geometry and magnetic field configuration of the proposed engine design. The goal here is to validate the computer models, to understand the plasma's behavior, and to develop the control algorithms that will be needed to operate the full-scale engine. This phase of testing will involve a host of sophisticated diagnostic instruments, laser interferometers to measure the plasma's density, Thomson scattering systems to measure its temperature, magnetometers to measure its magnetic field, all of which will generate a torrent of data that will be used to refine the design. Finally, there will be the testing of a full-scale integrated, ground-based prototype. This will be a device that is designed to achieve a net energy gain and to operate for long periods of time in a large vacuum chamber that simulates the space environment. The primary focus of this testing will be on demonstrating the reliability, the stability, and the long-term performance of the entire integrated system. It will involve a meticulous and painstaking process of slowly and carefully expanding the operational envelope of the engine, pushing it to higher power levels, to longer pulse lengths, and to a higher fusion energy gain. The measurement of the engine's propulsive performance will also be a major challenge. The thrust from a fusion engine will likely be much lower than that of a chemical rocket, but it will be sustained for a much longer time. Measuring this low, continuous thrust in a ground-based facility, where the engine is subject to the Earth's gravity and to interactions with the vacuum chamber walls, will require the development of new, highly sensitive thrust stands and diagnostic techniques. And throughout this entire multi-decade process, safety will be the overriding concern. The testing of a fusion engine will involve the handling of radioactive materials, the operation of high-power systems, and the generation of intense radiation. The safety protocols, the containment systems, and the emergency shutdown procedures will have to be designed and tested with a level of rigor that is unprecedented in the history of propulsion technology. The journey from a concept on a whiteboard to a tested, validated, and flight-ready fusion engine is one of the most daunting and complex technological paths that humanity has ever set out upon. But it is a path that is illuminated by the bright and steady light of the scientific method, a path that will be walked, step by careful, data-driven step, until we have finally mastered the power of the stars. The applications of advanced technology are transforming our exploration of space in ways that were science fiction just a generation ago, and nowhere is this more true than in the synergistic relationship between artificial intelligence and robotics. AI is becoming the brains of our robotic explorers, giving them a level of autonomy and intelligence that is essential for the exploration of distant and often unpredictable worlds. A spacecraft on a mission to Mars has a round-trip light time delay of up to 40 minutes, making real-time remote control from Earth an impossibility. The spacecraft must be able to make its own decisions, to navigate its own path, to diagnose its own problems, and to respond to unexpected events. This is where AI comes in. NASA's Perseverance rover on Mars is a prime example of this new generation of intelligent, robotic explorers. Its AutoNav system uses a pair of stereo cameras to create a three-dimensional map of the terrain in front of it, and then uses AI algorithms to analyze that map, to identify hazards like rocks and steep slopes, and to plot a safe and efficient path forward. This has allowed the rover to travel much further and faster than its predecessors, dramatically increasing its scientific return. The rover also uses AI in its scientific operations. An instrument called Aegis Autonomous Exploration for Gathering Increased Science uses machine learning algorithms to analyze the images from the rover's cameras, to identify geologically interesting targets, and to autonomously fire its laser spectrometer to analyze their chemical composition. This allows the rover to do a preliminary robotic triage of the landscape, ensuring that the limited and precious time for detailed scientific analysis is used on the most promising targets. This partnership between AI and robotics is not just limited to surface rovers. It is also essential for the operation of our space telescopes. The James Webb Space Telescope, for example, has a complex, multi-layered sunshield that must be kept perfectly oriented to protect its sensitive infrared detectors from the heat of the sun. This is a task that is managed by the spacecraft's autonomous attitude control system, which uses a combination of star trackers, gyroscopes, and AI-powered control algorithms to maintain the telescope's precise orientation with a stability that is almost beyond belief. Looking to the future, AI will become even more critical. The concept of swarm robotics is a particularly exciting one. Instead of sending a single, large, and expensive spacecraft to explore a planet or an asteroid, we could send a large number of small, cheap, and expendable robots that could work together, cooperatively, to achieve a common goal. They could form their own communication network. They could share information, They could collectively map a large area, and they could take risks that would be unacceptable for a single flagship mission. This kind of decentralized, emergent intelligence is a perfect application for AI. Another transformative technology is 3D printing, or additive manufacturing. The ability to print tools, spare parts, and even entire habitats in space, using a combination of pre-supplied materials and local in-situ resources, will be a game-changer for long-duration human missions. NASA has already tested a 3D printer on the International Space Station and is actively developing technologies for printing with lunar and Martian regolith. This will be essential for building a sustainable and less Earth-dependent human presence on other worlds. The development of reusable rocket technology, pioneered by companies like SpaceX, is another key piece of this puzzle. By dramatically lowering the cost of launching mass into orbit, reusability is making a whole new class of ambitious space missions economically feasible. It is the technology that will be needed to launch the large components of a future interplanetary spacecraft, and to build the in-space infrastructure of fuel depots and assembly stations that will be needed to support a thriving multiplanetary civilization. The future of space exploration will be a future of intelligent, autonomous, and cooperative robotic systems, of sustainable, in-space manufacturing, and of affordable and routine access to space. It is a future that is being built today, in the laboratories and the factories and the launch pads around the world. A future that will extend the reach of our senses, our intelligence, and our presence far beyond the confines of our home planet. The development of nuclear fusion propulsion will not just be a technological achievement, it will be a catalyst, a key that will unlock a whole new and ambitious era of space exploration missions. The combination of high speed and high efficiency that fusion offers will make missions that are currently on the speculative drawing board, or in the realm of science fiction, a tangible and achievable reality. A human mission to Mars is the most obvious and near-term beneficiary. Fusion propulsion would not just make the journey faster and safer, it would make it more sustainable. A fusion-powered spacecraft could carry a much larger payload, including the habitats, the life support systems, the scientific equipment, and the surface rovers needed to establish a true, long-term research outpost on the Red Planet. It could also provide a copious amount of power for the surface base itself, a Mars base in a box that would be essential for the early stages of settlement before large-scale in-situ power generation systems can be established. Beyond Mars, fusion would open up the entire outer solar system to a new level of intensive, and potentially human, exploration. The ocean worlds of Jupiter and Saturn Europa, Enceladus, and Titan are some of the most compelling targets in the search for life beyond Earth. A fusion-powered flagship mission, a large, sophisticated, and well-equipped spacecraft, could serve as a long-term orbiting base of operations in the Jovian or Saturnian system. It could deploy a series of smaller, specialized probes, landers to touch down on the icy surfaces, cryobots to melt their way through the ice shells, and autonomous submarines to explore the dark, mysterious oceans that lie beneath. This kind of systematic, multi-platform exploration is currently impossible with our power and mass-limited robotic missions. Fusion would make it a reality, and the dream of interstellar exploration, the ultimate human adventure, would finally move from the realm of the impossible to the realm of the merely incredibly difficult. A fusion-powered probe, perhaps using an advanced aneutron fuel and a direct-drive propulsion system, could be accelerated to a significant fraction of the speed of light, 10 to 20% or more. This would allow it to make the journey to our nearest stellar neighbor, the Alpha Centauri system, in a human lifetime, a journey of just 20 to 40 years. Such a mission, an interstellar precursor, would be a monumental, multi-generational undertaking, But it would be a mission of profound and enduring significance, a mission that would carry a piece of humanity, a piece of our knowledge, our culture, and our curiosity, out into the vast cosmic ocean that separates the stars. It would be the first tentative step in our journey to become a galactic species. But the applications of fusion are not just for the grand flagship missions. A compact, efficient fusion reactor could also revolutionize the more routine, workhorse missions of space exploration. It could power a new generation of powerful space-based telescopes, allowing us to see further and clearer than ever before. It could provide the power for a robust and high-bandwidth communication network that spans the entire solar system. It could power the robotic mining operations that will be needed to build an in-space economy. And it could provide a rapid interplanetary taxi service, ferrying crews and cargo between the Earth, the Moon, and Mars. The future that fusion propulsion enables is a future of abundance, an abundance of power, of speed, of access, and of possibility. It is a future where the solar system is no longer a vast, empty, and forbidding wilderness, but a rich, vibrant, and accessible frontier, a new home for the restless and insatiable spirit of human exploration. A human mission to Mars, powered by nuclear fusion, would be a spectacle of engineering and exploration unlike anything humanity has ever undertaken. It would be a journey that is not just faster, but fundamentally different from the long, slow coasting trajectories of our current chemical-powered missions. The spacecraft itself would be a marvel of design, a vessel assembled in Earth orbit, a true deep space cruiser. At its heart would be the fusion engine, a compact, powerful reactor, humming with the controlled fire of a miniature star. At the beginning of the journey, this engine would ignite, not in a violent, explosive burst, but in a steady, powerful, and continuous burn. The spacecraft would begin to accelerate, gently but relentlessly, at a constant 1G. For the crew inside, this would be a remarkable and transformative experience. After the initial, weightless period of orbital assembly, they would feel the familiar and comforting pull of gravity. They would be able to walk, to work, to eat, to sleep, in an environment that is, for all intents and purposes, identical to that on Earth. This would eliminate the debilitating physiological effects of prolonged microgravity, ensuring that the crew arrives at Mars strong, healthy, and ready for the challenges of surface exploration. For weeks, the engine would continue to fire, the spacecraft constantly accelerating, building up to an incredible velocity. The journey would be a busy one. The crew would not be passive passengers, but active scientists and explorers, conducting experiments, monitoring the spacecraft's systems, and observing their ever-changing view of the solar system. The vast amount of power from the fusion reactor would allow for a rich and comfortable living environment, with spacious habitats, advanced life support systems, and a high-bandwidth communication link back to Earth. At the midpoint of the journey, a delicate and precisely choreographed maneuver would take place. The spacecraft would flip, end over end, and the fusion engine would reignite, this time pointing in the direction of travel. The continuous 1G thrust would now be a deceleration, a gentle, steady braking that would slow the spacecraft down as it approached the red planet. After a total journey of just a few weeks, the spacecraft would gracefully enter orbit around Mars. The crew would then descend to the surface in a dedicated lander, leaving the fusion-powered mothership in orbit to serve as their power station, their communication hub, and their eventual ride home. The mission on the surface would be a new kind of exploration, not a brief, Apollo-style flags and footprints visit, but the establishment of a true, long-term research outpost, powered by the immense energy of the orbital fusion reactor. And when their work was done, the crew would ascend back to the mothership and begin the fast, 1G journey back to Earth. This is the vision of a fusion-powered Mars mission. It is a vision that transforms the journey from a perilous, survival-focused endurance test into a safe, efficient, and productive scientific expedition. It is a vision that requires a number of significant technological breakthroughs, from the development of a compact, reliable fusion engine to the creation of advanced, closed-loop life support systems. But it is a vision that is no longer in the realm of pure fantasy. It is a vision that is being actively pursued. In the laboratories and the design centers around the world, it is the next logical step in our long human journey of exploration, a step that will take us from being a planet-bound species to a true, multiplanetary one. The dream of interstellar travel, of crossing the vast, dark ocean that separates the stars, is perhaps the most powerful and enduring dream in all of science fiction, and in all of human aspiration. With our current technology, it is a dream that is hopelessly out of reach. The distances are simply too great, the travel times too long. But nuclear fusion is the one technology we can currently conceive of that could, in principle, make this dream a reality. A fusion-powered interstellar probe would be a machine of incredible power and endurance, a vessel designed to travel for decades, or even centuries, through the cold, empty void of interstellar space. The key to interstellar travel is achieving an incredibly high exhaust velocity, and therefore an incredibly high specific impulse. The deuterium-tritium fuel cycle, while powerful, may not be efficient enough for a true interstellar mission. The ideal interstellar engine would likely use an advanced aneutron fuel, like deuterium-helium-3 or proton-boron. These reactions release most of their energy in the form of high energy, charged particles, which can be directly funneled and accelerated by a magnetic nozzle, achieving an exhaust velocity that is a significant fraction of the speed of light. An interstellar spacecraft powered by such an engine would not be a conventional rocket. It would be a beam-powered vessel. The engine would generate a powerful relativistic jet of plasma, and the thrust would come from the momentum of this jet. To reach a truly interstellar speed on the order of 10% of the speed of light, the spacecraft would need to accelerate continuously for many years. The engineering challenges are, of course, immense. The engine would need to be incredibly reliable, capable of operating autonomously for the entire duration of the multi-decade journey. The spacecraft would need to be protected from the harsh environment of interstellar space, including the constant bombardment of high-energy cosmic rays and the potential for impacts with interstellar dust grains at relativistic speeds. A single grain of dust hitting a spacecraft traveling at 10% of the speed of light would have the kinetic energy of a large conventional explosion. This would require the development of robust, multi-layered shielding and perhaps even an active deflector shield using powerful magnetic or laser fields. Another major challenge is the fuel. While a fusion engine is incredibly efficient, a multi-decade journey of constant acceleration would still require a significant amount of fuel. The concept of an interstellar ramjet, first proposed by the physicist Robert Bussard, offers a potential solution. A ramjet would use a massive, forward-facing magnetic scoop to collect the sparse hydrogen of the interstellar medium and use it as fuel for its fusion engine. This would be the ultimate in-situ resource utilization, a ship that literally drinks its fuel from the empty space it travels through. While the physics of a Bussard ramjet is incredibly challenging, it remains one of the most elegant and compelling concepts for true long-range interstellar travel. The first interstellar missions will almost certainly be unmanned, robotic probes, our robotic emissaries to the stars. They would be our eyes and ears in a new and unexplored cosmic territory, sending back the first precious data about the conditions around another star, about the properties of its planets, and perhaps about the existence of life. A human interstellar mission is a dream for a much more distant future, a multi-generational undertaking that would require a level of technological mastery and societal commitment that is currently far beyond us. But it is a dream that is not impossible. The same laws of physics that power our sun can, in principle, be harnessed to build a starship. The journey will be long, the challenges will be great, but the lure of the stars is a powerful and enduring one: fusion. Propulsion is the technology that could, one day, allow us to answer that lure, to take our first tentative steps out of our solar system, and to begin our journey to become a true galactic civilization. The exploration of the cosmos, from our own solar system to the distant stars, is not just a scientific and technological endeavor, it is also a profoundly ethical one. As we develop the capacity to travel to, and to interact with, other worlds, we are confronted with a new set of moral responsibilities and a new class of ethical dilemmas. The concept of planetary protection is at the heart of these concerns. This is the principle that we must take all necessary precautions to avoid contaminating other, potentially life-bearing, worlds with terrestrial microbes. A world like Mars or the subsurface ocean of Europa may harbor its own indigenous life. And this life, if it exists, would be one of the most profound and precious discoveries in the history of science. The accidental introduction of hardy, Earth-based bacteria could have a devastating impact on such an alien ecosystem, outcompeting the native life and potentially destroying it before we have even had a chance to discover it. This would be a scientific tragedy of cosmic proportions. For this reason, all robotic missions to potentially habitable worlds are subjected to a rigorous process of sterilization, and there are strict international protocols that govern their design and operation. But the challenge will become even greater when we begin to send human missions to these worlds. Humans are walking, talking ecosystems, teeming with trillions of microbes. It is impossible to completely sterilize a human crew. And so, a human mission to Mars will inevitably introduce a host of terrestrial organisms into the Martian environment. This raises a deep and difficult ethical question. Do we have the right to do this? Do we have the right to risk contaminating another world, even for the sake of exploration and discovery? The other side of the planetary protection coin is back contamination, the risk of bringing an extraterrestrial organism back to Earth. While the chances of an alien microbe being harmful to our terrestrial ecosystem are likely very small, they are not zero. The consequences of such an event could be catastrophic. This is why any mission that returns samples from a potentially habitable world, like the planned Mars sample return mission, will be subject to the most stringent quarantine and containment protocols imaginable. Beyond the issue of microbial contamination, there is the larger question of our long-term environmental impact on other worlds. If we one day establish a permanent industrial presence on the Moon or Mars, how do we do so in a way that is sustainable and responsible? Do we have the right to strip mine the Moon for its resources? Or to terraform Mars? To fundamentally and irrevocably alter its environment to make it more like Earth? These are questions that echo the environmental debates we are having here on our own planet, but they are writ large on a cosmic scale. They force us to think about our long-term relationship with the cosmos and to decide whether we will be a species that explores with a sense of stewardship and respect, or one that simply expands and exploits. The commercialization of space raises another set of ethical challenges. As private companies begin to develop the capacity for space mining and for space tourism, we are confronted with questions of equity, of access, and of ownership. Who owns the resources of the Moon and the asteroids? The Outer Space Treaty of 1967 declares that celestial bodies are not subject to national appropriation, that they are the province of all mankind. But how this principle will be applied in an era of private enterprise is a complex and unresolved legal and ethical issue. Will the benefits of space resources be shared for the good of all humanity? Or will they be concentrated in the hands of a few powerful corporations and spacefaring nations, creating a new and even more extreme form of inequality? And who gets to decide the rules? The development of a robust and equitable framework for international space law and governance is one of the most urgent and important tasks of the 21st century. The journey into space is not just a journey outwards, it is also a journey inwards. It is a journey that forces us to confront our deepest values, our highest aspirations, and our greatest responsibilities. It is a journey that will test not just our technology, but also our wisdom and the choices we make in the coming decades. As we stand on the threshold of becoming a truly multiplanetary species, will have consequences that will echo for generations and perhaps even eons to come. The use of nuclear technology in space, from the small, fission-based radioisotope power sources that have been the workhorse of our deep space robotic missions, to the large, powerful fusion engines that may one day propel our starships, is a subject that is fraught with a unique and potent set of ethical concerns. It is a technology that offers both immense promise and profound peril, and it requires a level of caution, of foresight, and of international cooperation that is unprecedented in the history of exploration. The primary ethical concern is, of course, safety. The launch of any nuclear material into space carries with it the risk, however small, of a launch failure. An accident that could disperse radioactive material into the Earth's atmosphere or oceans. This is a risk that has been managed successfully for decades with the use of RTGs, which are designed to be incredibly robust and to withstand the catastrophic failure of a rocket launch. But the much larger and more powerful nuclear reactors that would be needed for propulsion would require an even higher level of safety engineering and a new, more rigorous set of international launch protocols. There is also the long-term ethical consideration of space debris. A nuclear-powered spacecraft, at the end of its mission, becomes a piece of radioactive space junk. While this is less of a concern for missions that are sent into the outer solar system or onto an interstellar trajectory, it is a major concern for missions that operate in the increasingly crowded environment of Earth orbit. The safe and responsible disposal of spent nuclear reactors in space, perhaps by sending them into a stable, high-altitude graveyard orbit, will be an essential part of any future nuclear propulsion architecture. The governance of nuclear technology in space is another critical ethical issue. The Outer Space Treaty of 1967, the foundational document of international space law, prohibits the placing of nuclear weapons or any other kinds of weapons of mass destruction in orbit or on celestial bodies. But the line between a peaceful nuclear propulsion system and a potential weapon can be a blurry one. A powerful, high-thrust fusion engine could, in principle, be used to rapidly move a military asset, or to deorbit an opponent's satellite. The development of these technologies will require a new era of transparency, of verification, and of arms control in space to ensure that the final frontier does not become the next great battlefield. The societal implications and the issue of public perception are also crucial. The word nuclear carries with it a heavy and often negative emotional and historical baggage. The public's fear of nuclear technology, born from the legacy of Hiroshima, of Chernobyl, of Fukushima, is a real and powerful political force. A successful and sustainable program of nuclear space exploration will require a deep and sustained effort of public education and engagement. It will require scientists and engineers to be open and transparent about both the immense benefits and the real, if manageable, risks of these technologies. It will require a new level of dialogue between the scientific community, the policymakers, and the public. A dialogue that is based on trust, on evidence, and on a shared vision of a hopeful and inspiring future in space. Finally, There is the question of intergenerational ethics. The decisions we make today about the use of nuclear technology in space will have consequences that will last for generations to come. The long-lived radioactive materials we place in space will be a legacy that we leave for our descendants. We have a profound ethical responsibility to ensure that this legacy is one of a new era of exploration and opportunity, and not one of a new and enduring environmental hazard. The journey to a nuclear-powered future in space is a journey that must be walked with a deep sense of ethical responsibility. A journey where every step is guided by the principles of safety, of sustainability, of peace, and of a shared commitment to the long-term well-being of our species and our cosmic home. The comparison between the waste produced by nuclear fission and nuclear fusion is one of the most compelling and important arguments for the long-term pursuit of fusion energy. It is a comparison that highlights a fundamental difference in the underlying physics of the two processes. A difference that has profound implications for the environmental and intergenerational legacy of nuclear power. Nuclear fission, the splitting of a heavy nucleus like uranium, is an inherently messy process. The fission of a uranium nucleus produces not just two smaller fission product nuclei, but a whole spectrum of different and often highly radioactive isotopes. These fission products, like cesium-137 and strontium-90, are the primary source of the intense, short-term radioactivity of spent nuclear fuel. But the fission process also produces transuranic elements, heavy nuclei like plutonium, americium, and neptunium, which are formed when the uranium fuel absorbs a neutron without fissioning. These transuranic elements are alpha emitters, and they have incredibly long half-lives, on the order of thousands, or even hundreds of thousands, of years. It is these long-lived actinides that constitute the true long-term challenge of high-level nuclear waste disposal. This waste must be isolated from the biosphere for a period of time that is longer than the entire recorded history of human civilization. A challenge that requires the development of deep geological repositories, a solution that has proven to be both technologically difficult and politically contentious. Nuclear fusion, the merging of light nuclei, is a much cleaner and more elegant process. The primary fusion reaction that will be used in the first generation of fusion power plants, the deuterium-tritium reaction, produces only two particles, a single helium nucleus, which is a harmless, inert gas, and a single high-energy neutron. There are no fission products, no long-lived transuranic waste. The primary radiological issue in a fusion reactor is the activation of the structural materials of the reactor itself by the constant bombardment of these high-energy neutrons. The neutrons can knock the nuclei of the steel and other materials in the reactor wall out of their stable configuration, transforming them into radioactive isotopes. This means that at the end of its life, the structure of a fusion reactor will be radioactive and will need to be disposed of as low-level or intermediate-level waste. However, this is a fundamentally different and much more manageable problem than the waste from a fission reactor. The volume of activated material from a fusion plant will be comparable to that from a fission plant, but the radioactivity itself will be much less intense and will decay much more quickly. By carefully choosing low activation materials for the reactor structure, such as advanced steels or silicon carbide composites, it is possible to design a fusion reactor where the radioactivity of the components will decay to a level that is safe for recycling or shallow land burial within about 100 years. This is a timescale that is within the realm of normal human engineering and institutional control, a stark contrast to the multi-millennial timescale of fission waste. Furthermore, the aneutronic fusion reactions, like deuterium-helium-3 or proton-boron, which are the long-term goal of fusion research, would produce even less radioactive waste. A proton-boron reactor, in principle, would produce no neutrons at all, meaning the activation of the reactor structure would be almost completely eliminated. This is the ultimate dream of clean nuclear energy, a power source that is not just carbon-free, but that leaves behind no long-term radioactive legacy for future generations. The difference between fission and fusion waste is not just a quantitative one, it is a qualitative one. It is the difference between a technology that creates a multi-generational environmental and ethical burden, and one that offers the promise of a truly sustainable and responsible energy future. It is one of the primary reasons why the long, difficult, and expensive quest to master the power of fusion is a quest that is so profoundly worth pursuing. The future of space exploration is not just about building better rockets. It is about building a new, sustainable, and self-sufficient human presence beyond the Earth. And the key to this future lies in the concept of in situ resource utilization. ISRU, the art of living off the land, of using the resources that are available in space to support our exploration and our settlement of other worlds. For most of the space age, we have operated on an expeditionary model. We have packed everything we need, our habitats, our life support, our food, our fuel into a cosmic suitcase, and have carried it with us from Earth. This is an incredibly expensive and inefficient way to explore. Every kilogram of mass that we launch from Earth's deep gravity well comes at a high price, both in terms of energy and in terms of money. The future of a sustainable, multi-planetary human presence depends on our ability to break free from this terrestrial supply chain, to learn to use the abundant resources of the Moon, of Mars, and of the asteroids. The most important of these resources is water. Water is the elixir of life, essential for drinking, for growing food, and for providing breathable air through electrolysis, which splits water into hydrogen and oxygen. But it is also the raw material for rocket propellant. Hydrogen and oxygen are the most efficient chemical rocket propellants we know. The discovery in recent years of vast deposits of water ice in the permanently shadowed craters at the poles of the Moon and in the subsurface ice sheets of Mars has been a game changer. It means that future lunar and Martian outposts could, in principle, produce their own air, their own water, and their own rocket fuel. A lunar base could become a gas station in space, a place where spacecraft on their way to Mars or the outer solar system could top up their tanks, dramatically reducing the amount of propellant that needs to be launched from Earth. The regolith, the soil of the Moon and Mars, is another valuable resource. It is rich in oxides of silicon, aluminum, iron, and titanium, which can be processed to extract these metals for manufacturing and construction. Using techniques like 3D printing with molten regolith, future settlers could build their own habitats, their own landing pads, their own radiation shields, using the local dirt. This would dramatically reduce the mass of the infrastructure that needs to be transported from Earth. The atmospheres of other worlds are another potential resource. The thin carbon dioxide-rich atmosphere of Mars, for example, can be used as a feedstock for producing both oxygen for life support and methane for rocket fuel, a process that is being demonstrated by the MOXIE experiment on the Perseverance rover. The even thicker, nitrogen-rich atmosphere of Titan could be a source of breathable air for a future outpost, and the advanced aneutron fusion fuels that may one day power our starships are also present in space. Helium-3, as we have seen, is abundant on the Moon, and deuterium is present in the water ice of the Moon and Mars, and in the vast atmospheres of the gas giants. A mature, solar system-wide civilization could have a complex and interconnected economy, with water being mined from the poles of the Moon, with metals being extracted from the asteroids, and with fusion fuels being harvested from the atmosphere of Jupiter. This is a long-term vision, a multi-generational project. It will require the development of a host of new robotic and autonomous technologies for prospecting, for mining, for processing, and for manufacturing in the harsh and unforgiving environment of space. But it is a vision that is not just about economics or logistics. It is a vision that is about freedom. It is the vision of a future where humanity is no longer a species confined to a single, fragile planet, but is a true, multiplanetary species. With the resilience, the robustness, and the freedom that comes from having a presence on multiple worlds. It is the vision of a future where we are no longer just visitors in space, but are truly at home in the solar system. The dream of a human presence on Mars, of a red planet that is home to a new branch of our civilization, is one of the most powerful and enduring visions in the story of space exploration. And fusion propulsion is the technology that could finally transform this dream from a distant, aspirational goal into a tangible, achievable reality. A crewed mission to Mars is a challenge of a completely different order of magnitude than the Apollo missions to the Moon. The distances are 100 times greater. The travel times are measured in months rather than days, and the mission duration is measured in years rather than weeks. The challenges of radiation, of microgravity, of life support, of psychological stress are all an order of magnitude more severe. A fusion-powered spacecraft would address these challenges at their very root. By cutting the transit time from many months to just a few weeks, it would dramatically reduce the crew's exposure to the two greatest physiological dangers of interplanetary space: cosmic radiation and weightlessness. A shorter journey would also reduce the psychological strain of confinement and isolation, and it would simplify the logistics of the mission, reducing the total amount of supplies that need to be carried. A fusion-powered Mars transport vehicle would not be a cramped, minimalist capsule, but a large, spacious, and well-equipped vessel, a true home for the crew during their journey. The immense power output of the fusion reactor would allow for a robust, closed-loop life support system, for spacious living quarters, and for a powerful radiation shield, perhaps an active one using magnetic fields. And as we have seen, a constant thrust trajectory could provide a continuous 1G artificial gravity, completely eliminating the problems of microgravity and allowing the crew to arrive at Mars in peak physical condition. The fusion engine would not just be for the interplanetary transit, it would also be a critical asset in the Martian system itself. A high-power fusion reactor, either on the transport vehicle in orbit or on a dedicated lander on the surface, could provide the kilowatts and even megawatts of electrical power that would be needed to support a permanent human research outpost. It could power the life support systems, the scientific laboratories, the in-situ resource utilization plants that will produce water and fuel from the Martian environment, and the surface rovers that will explore the surrounding landscape. It would be the heart of a new, human civilization on another world. The development of fusion propulsion would also change the very philosophy of Mars exploration. With chemical rockets, a human mission to Mars is a massive Apollo-style, flags and footprints undertaking, a mission so complex and expensive that it can only be done once in a generation. With fusion propulsion, the journey to Mars would become a routine and sustainable enterprise. A fleet of reusable, fusion-powered Mars clippers could establish a continuous Earth-Mars bridge, ferrying crews and cargo back and forth on a regular and predictable schedule. This would allow for the gradual, incremental, and sustainable buildup of a permanent and eventually self-sufficient human presence on the red planet. This is the future that fusion enables. It is a future where the first tentative human footsteps on another planet are not the culmination of our journey into space, but are just the beginning. It is a future where Mars is not just a destination to be visited, but a new world to be explored, to be understood, and to one day be called home. The journey to the stars, the dream of sending a human or a robotic emissary to another solar system, is the ultimate expression of our exploratory impulse. It is a challenge of such immense scale and difficulty that it pushes the very limits of our science, our technology, and our imagination. But it is a challenge that fusion propulsion, and only fusion propulsion, could one day allow us to meet. The distances are almost beyond comprehension. Proxima Centauri, the nearest star to our Sun, is over 4 light-years away, about 25 trillion miles. To travel this distance in a reasonable amount of time, a spacecraft would need to achieve a velocity that is a significant fraction of the speed of light, and this requires a propulsion system with an incredibly high specific impulse and a colossal amount of energy. A fusion engine is the only technology we can currently conceive of that could, in principle, meet these requirements. The ideal interstellar engine would be a direct drive system, one that uses an advanced aneutron fusion fuel, like deuterium-helium-3. In such an engine, the high-energy, charged particles from the fusion reaction would be channeled and accelerated by a powerful magnetic nozzle, creating a relativistic jet of plasma. A spacecraft powered by such an engine could, in theory, be accelerated to 10, 20, or even 30% of the speed of light. At these speeds, a journey to Alpha Centauri would take not millennia, but decades. A timescale that is within the realm of a long-term robotic mission, or even a multi-generational human one. The design of such an interstellar probe, a true starship, would be a monument to human ingenuity. It would be a completely autonomous, self-contained world, a robotic ark designed to travel for a century or more through the cold, dark, and empty void of interstellar space. It would need a power source that could operate reliably for its entire journey, not just for propulsion, but also to power its scientific instruments, its communication system, and its own intelligent onboard mind. The fusion reactor itself would be this heart. It would also need a way to protect itself from the hazards of interstellar travel. At relativistic speeds, even a tiny grain of interstellar dust becomes a lethal projectile. The spacecraft would need a robust, multi-layered shield to absorb these impacts, and perhaps even an active deflector shield, a powerful magnetic or laser field that could push the dust out of its path. And it would need a way to communicate its findings back to Earth across the vast light-year gulf. This would require a large, powerful antenna and a laser communication system of unprecedented power and precision. The scientific payoff of such a mission would be incalculable. It would give us our first close-up look at another solar system. It would allow us to study the properties of its star, to search for planets in its habitable zone, and to analyze their atmospheres for the signs of life. It would be the moment when we finally, definitively, answer the question of whether we are alone in the universe. A human, interstellar mission is a dream for a much more distant, and perhaps even unattainable, future. The challenges of life support, of radiation shielding, of psychology, of sociology are an order of magnitude greater than for a robotic mission. It would likely require a world ship, a massive, self-sustaining ecosystem designed to support a human community for many generations. It is a vision that is as much a social and a philosophical challenge as it is a technological one. But the dream of interstellar travel is a powerful and important one. It is a dream that pulls us forward, that inspires us to be better, to be smarter, to be more far-sighted. It is a dream that reminds us that our potential is not limited to this single, fragile world, and fusion propulsion is the technology that keeps this dream alive, the technology that gives it a grounding in the real, and not just the imagined possibilities of physics. It is the key that could one day unlock the door to a truly galactic future for humanity. As we stand on the threshold of a new era of space exploration, an era that may be powered by the cosmic fire of fusion, We are confronted not just with immense technological and scientific challenges, but also with a profound set of environmental and ethical responsibilities. The journey into space is not just a journey of discovery. It is a journey that will test our wisdom, our foresight, and our capacity for responsible stewardship of the new worlds we encounter. The problem of space debris is a stark and immediate reminder of this responsibility. The near-Earth orbital environment is already a celestial junkyard, littered with thousands of defunct satellites, spent rocket stages, and millions of smaller fragments from past collisions and explosions. This debris travels at incredible speeds, and even a tiny fleck of paint can have the impact of a hand grenade, posing a serious threat to operational satellites and to the International Space Station. The Kessler Syndrome, the frightening possibility of a runaway cascade of collisions that could render certain orbits unusable for generations, is no longer a distant, theoretical concern. It is a clear and present danger. As we launch new, large-scale satellite constellations and plan for a future of more routine access to space, we must develop and implement a robust and internationally agreed-upon framework for space traffic management and debris mitigation. This will require new technologies for tracking small debris, for deorbiting defunct satellites, and perhaps one day for actively removing the existing debris from orbit. Beyond our own orbital backyard, there is the even more profound ethical challenge of planetary protection as we send our robotic and, eventually, our human emissaries to other worlds, particularly to those that may harbor life, like Mars or Europa. We have a profound moral and scientific obligation to do so responsibly. We must avoid forward contamination, the introduction of terrestrial microbes that could harm or outcompete any indigenous life, and we must also protect our own biosphere from back contamination. The potential, however remote, of bringing a harmful extraterrestrial organism back to Earth. This requires a level of meticulous sterilization and quarantine that is on the very cutting edge of our technological capabilities. The commercialization of space, while a powerful engine of innovation and progress, also brings with it a new set of ethical dilemmas. The prospect of mining the moon and the asteroids for their valuable resources raises deep questions about ownership, about equity, and about environmental stewardship. Who has the right to profit from these celestial resources? The Outer Space Treaty of 1967 declares that space is the province of all mankind, but the legal and ethical framework for how this principle will be applied in an era of private commercial activity is still being written. We have a historic opportunity to ensure that the benefits of space resources are shared equitably for the good of all humanity, and to avoid repeating the mistakes of our own, often destructive, history of terrestrial resource exploitation. The long-term vision of terraforming Mars, of transforming it into a second, habitable Earth, is perhaps the ultimate ethical challenge. Do we have the right to fundamentally and irrevocably alter the environment of another world? Even if it is to create a new home for humanity, this is a question that forces us to grapple with our own deepest values and with our ultimate relationship with the cosmos. Are we the gardeners of the solar system, with a right and a responsibility to spread life wherever we can? Or are we the custodians, with an obligation to preserve the pristine, natural state of the worlds we explore? The journey into space is a journey that is not just changing our understanding of the universe, it is also changing our understanding of ourselves. It is forcing us to think on longer timescales, on a planetary and even a cosmic scale. It is forcing us to become a more mature, more responsible, and more ethically aware species. And the choices we make in the coming decades as we stand on this new and exciting frontier will define not just our future in space, but the very future of the human spirit. The use of nuclear fusion in space, while offering a vision of a clean and powerful future, is not without its own unique set of environmental considerations. While it is true that fusion is a fundamentally cleaner process than fission, producing no long-lived, high-level radioactive waste. It is not completely free of radiological and environmental challenges. The primary environmental issue for a deuterium-tritium fusion engine is the management of the tritium fuel and the activation of the reactor's structural materials. Tritium is a radioactive isotope of hydrogen, and while it is a low-energy beta emitter with a relatively short half-life, it is also a highly mobile element that can be difficult to contain. A fusion-powered spacecraft would need to have a robust and highly reliable system for storing, handling, and recycling the tritium fuel, with multiple layers of containment to prevent any accidental release into the spacecraft's habitat or into the external space environment. The activation of the reactor's structure by the high-energy neutrons from the DT reaction is a more significant long-term environmental issue. The materials of the first wall and the breeding blanket will, over time, become radioactive. While this radioactivity is much less intense and much shorter-lived than the waste from a fission reactor, it is still a source of low-level and intermediate-level waste that will need to be managed responsibly at the end of the spacecraft's life. The development of low-activation materials is a key part of the strategy to mitigate this problem. And for a spacecraft that is designed to be reusable or to be serviced in orbit, the ability to remotely and robotically handle and replace these activated components will be an essential part of the design. The long-term environmental impact of a fleet of fusion-powered spacecraft on the solar system environment is another consideration. While the primary byproduct of the DT reaction is harmless helium, a large number of fusion rockets operating over many decades would release a significant number of high-energy neutrons into the space environment. The long-term effect of this on the magnetospheres of planets or on the radiation environment of cislunar space is something that would need to be studied and understood. The sourcing of the fusion fuel also has potential environmental implications. While deuterium can be easily extracted from the water on Earth, the primary source of lithium, which is needed to breed tritium, is terrestrial mining, a process that has its own environmental footprint. The long-term vision of mining the moon for helium-3 would also have a significant environmental impact on the lunar landscape. Any large-scale in-space resource utilization will need to be done with a strong sense of environmental stewardship, with clear international agreements on how to minimize the impact on these pristine, celestial bodies. These are all real and important challenges, but they are also manageable. Engineering challenges. They are challenges that can be addressed through careful design, through the development of new materials and technologies, and through the creation of a robust and responsible regulatory framework. The environmental benefits of fusion, both on Earth and in space, are so profound that they make the effort to overcome these challenges a deeply worthwhile one. Fusion offers the promise of a future where our exploration of the cosmos is not limited by the dirty, inefficient, and finite energy source of chemical combustion, but is powered by the same clean, sustainable, and awe-inspiring process that powers the stars themselves. It is a future where our journey to the stars is not in conflict with our responsibility to protect our own fragile, pale blue dot. The use of any form of nuclear technology in space is a subject that is, and should be, a matter of deep and serious ethical consideration. It is a technology that holds the key to unlocking the solar system. But it is also a technology that carries with it a unique set of risks and a profound sense of responsibility. The primary ethical concern, as we have seen, is safety, particularly the safety of the public on Earth during a launch. The launch of a spacecraft containing a significant amount of nuclear material, whether it is the plutonium in an RTG or the tritium fuel in a fusion engine, will always carry the risk, however small, of a catastrophic launch failure that could disperse this material into the environment. This risk requires an incredible level of engineering rigor, of redundant safety systems, and of transparent and internationally agreed-upon launch protocols. The decision to accept this risk must be made with a clear-eyed and honest assessment of the immense scientific and exploratory benefits that the mission will provide. Beyond the issue of launch safety, there is the broader ethical question of the governance of nuclear technology in space. The Outer Space Treaty of 1967, the foundational document of international space law, was written in the shadow of the Cold War, and its primary concern was to prevent the militarization of space, particularly the placement of nuclear weapons in orbit. But the treaty also lays out a set of broader ethical principles for the exploration of space that it should be carried out for the benefit and in the interests of all countries. That space is the province of all mankind, and that states are responsible for the national activities in space, whether they are carried out by governmental agencies or by non-governmental entities. These principles will be put to the test in the coming era of nuclear space exploration. The development of powerful nuclear propulsion systems, like a fusion engine, could have a dual-use potential. A technology that can rapidly move a large spacecraft to Mars could also be used to rapidly move a military asset. The international community will need to develop new and robust frameworks for transparency, for verification, and for arms control to ensure that the final frontier does not become the next great battlefield. The societal implications and the issue of public perception are also a critical part of the ethical landscape. The public's relationship with nuclear technology is a complex and often emotional one. There is a deep-seated and understandable fear of the unknown, a fear that has been shaped by the history of nuclear weapons and by the accidents at Chernobyl and Fukushima. A successful and sustainable program of nuclear space exploration will require a new kind of dialogue between the scientific community, the policymakers, and the public. It will require a commitment to radical transparency, to an open and honest discussion of both the benefits and the risks. And it will require the creation of a compelling and inspiring narrative, a narrative that can help the public to see that the responsible use of nuclear technology in space is not a threat to our future, but is, in fact, one of the keys to ensuring it. Finally, there is the profound ethical question of our long-term cosmic destiny. The development of fusion propulsion and other advanced nuclear technologies will give us a level of power and influence over our environment that is unprecedented in our history. It will give us the ability to travel between the planets, to mine the resources of the asteroids, to build permanent settlements on other worlds, and perhaps, one day, to even engineer the environments of those worlds to make them more like our own. This is a godlike power, and it comes with a godlike responsibility. What kind of cosmic civilization do we want to become? Will we be a species that expands with wisdom, with foresight, with a sense of reverence for the beauty and the integrity of the worlds we encounter? Or will we be a species that simply repeats the mistakes of our own, often destructive, terrestrial history on a new and grander cosmic stage? These are the ethical questions that will define our future in space. They are questions that do not have easy answers. But they are questions that we must begin to ask, with a sense of humility, of urgency, and of a shared commitment to building a future that is worthy of the vast and wonderful universe that has given us the gift of a conscious and questioning existence. The profound difference between the waste produced by nuclear fission and nuclear fusion is not just a technical detail. It is a fundamental distinction that goes to the very heart of the long-term sustainability and the ethical legacy of nuclear power. It is the difference between a technology that creates a multi-millennial burden for future generations and one that offers the promise of a truly clean and responsible energy source. Nuclear fission, the process of splitting heavy atoms, is an inherently messy affair. The fission of a uranium nucleus produces a wide and unpredictable spectrum of lighter fission product isotopes, Many of these, like cesium-137 and strontium-90, are highly radioactive and are the primary source of the intense short-term heat and radiation of spent nuclear fuel. But the even greater long-term challenge comes from the transuranic elements, heavy nuclei like plutonium and americium, which are formed when the uranium fuel captures a neutron without fissioning. These transuranic elements are incredibly long-lived, with half-lives that can be tens of thousands, or even millions, of years. It is these long-lived actinides that constitute the true, enduring problem of high-level nuclear waste. This waste must be isolated from the biosphere in deep geological repositories, a solution that is both technologically challenging and politically difficult to implement. It is a legacy that we are, in a very real sense, leaving to our distant, and perhaps incomprehensible, descendants. Nuclear fusion, on the other hand, is a process of elegant simplicity. The primary deuterium-tritium reaction produces only two particles, a stable, harmless helium nucleus and a single, high-energy neutron. There are no fission products, no long-lived transuranic waste. The primary radiological issue is the activation of the reactor's structural materials by these neutrons. This is a real and important challenge, but it is a challenge of a completely different order of magnitude. The activated materials in a fusion reactor will be classified as low-level or intermediate-level waste, not high-level waste, and the radioactivity will decay to a safe, background level in a matter of decades, or at most, a century or two. Not millennia. This is a timescale that is within the realm of normal human engineering and institutional control. Furthermore, the volume of this waste will be comparable to that of a fission plant, and the materials themselves are not the exotic, weapons-usable materials like plutonium. By developing advanced, low-activation materials, it may even be possible to design a fusion reactor where the components can be recycled after a relatively short cooling-off period. And the long-term dream of aneutronic fusion, using fuels like deuterium helium-3 or proton-boron, would eliminate the neutron problem almost entirely, leading to a power source that is, for all practical purposes, free of any long-term radioactive waste. This is not just a quantitative difference. It is a profound, qualitative, and ethical difference. It is the difference between a technology that solves our present energy problems by creating a new and enduring problem for the future, and a technology that offers a truly sustainable solution. It is the difference between burdening our children with a toxic legacy and bequeathing them a clean and hopeful future. The journey to fusion is a long and difficult one, but it is a journey that is driven, at its deepest level, by this profound ethical imperative to find a way to power our civilization that is in harmony with the long-term well-being of our planet and of all the generations that will come after us. Imagine a force so pervasive, so quietly influential, that it shapes the very fabric of our universe, yet remains entirely invisible to the naked eye. This unseen power is the magnetic field, a silent architect of the cosmos. It is a region in space where magnetic forces manifest, born from the simple movement of electric charges. Yet its influence is anything but simple. These fields are omnipresent, weaving a vast, interconnected web that stretches across the desolate emptiness of intergalactic space, sweeps through the majestic, spiraling arms of galaxies, and cloaks the stars, planets, and even the enigmatic black holes that populate our universe. Though we cannot see them, their presence is undeniable, their effects profound. They are the gentle hand that guides the birth of stars, the powerful current that steers high-energy cosmic rays, and the invisible shield that protects worlds like our own from the relentless fury of their suns. From the smallest molecular clouds where new stars are forged, to the largest clusters of galaxies bound together by gravity, Magnetic fields are the unseen wiring of the cosmos, the silent, omnipresent force that brings order to chaos and sculpts the grand cosmic tapestry we are only just beginning to comprehend. To understand these fields is to peel back a layer of reality, to glimpse the invisible architecture that underpins all of existence. This invisible architecture is not an abstract, distant phenomenon. It is a force that is intimately connected to our own existence, a silent guardian that makes life on Earth possible. Our planet is a magnetic world, a giant, spinning dynamo that generates a powerful magnetic field extending far out into space, creating a protective bubble known as the magnetosphere. This field is not a static entity. It is a dynamic, ever-changing shield, born from the churning, convective motions of molten iron and nickel deep within the Earth's outer core. This process, known as the geodynamo, transforms the planet's rotational and thermal energy into a vast, planetary-scale magnetic field. A field that is as essential to our survival as the air we breathe and the water we drink. The sun, our life-giving star, is a source of constant and often violent activity. It continuously emits a stream of charged particles, protons, and electrons known as the solar wind. This wind travels outwards through the solar system at hundreds of kilometers per second, a relentless supersonic gale that would, if left unchecked, strip away our planet's atmosphere over geological timescales, leaving us a barren and lifeless rock, much like our celestial neighbor, Mars. But Earth's magnetic field stands as a silent sentinel against this cosmic onslaught. The magnetosphere deflects the vast majority of the solar wind particles, forcing them to flow around our planet like water around a boulder in a stream. This constant invisible battle in the space around our planet is what preserves our fragile atmosphere, protecting the delicate conditions that have allowed for the evolution and flourishing of life. We owe our very existence to this invisible magnetic shield. But the interaction between Earth's magnetic field and the solar wind is not just a story of protection. It is also a source of breathtaking beauty. Occasionally, some of the charged particles from the solar wind are trapped by the magnetosphere and are funneled down along the magnetic field lines towards the Earth's polar regions. As these high-energy particles collide with the atoms and molecules of our upper atmosphere, primarily oxygen and nitrogen, they excite them, causing them to glow. The result is one of nature's most spectacular displays, the aurora borealis in the north and the aurora australis in the south. These dancing, shimmering curtains of green, pink, and violet light are a stunning, visible manifestation of the invisible forces that govern our planet's interaction with the sun. They are a breathtaking reminder that we live within a dynamic electromagnetic environment and that the universe, even in its most violent aspects, can create moments of profound and ethereal beauty. The auroras are the poetry of planetary physics, a silent symphony played out in the polar skies, a testament to the power and the elegance of the magnetic field that keeps our world alive. The story of planetary magnetic fields is a story of diversity. When we look at our solar system, we see a veritable zoo of different magnetic worlds, each telling a unique story of its own internal dynamics and its evolutionary history. Jupiter, the king of the planets, boasts the most powerful magnetic field in our solar system, a field that is nearly 20,000 times stronger than Earth's. This immense field is not generated by molten iron, but by a vast, deep ocean of metallic hydrogen, a strange, exotic state of matter that is formed under the crushing pressures of Jupiter's interior. This mighty magnetosphere creates intense radiation belts that are a serious hazard for any spacecraft that ventures too close, and it drives spectacular, planet-sized auroras at Jupiter's poles. It even has a profound influence on its moons, like the volcanically active Io, whose fiery eruptions are thought to be, in part, fueled by the intense magnetic and electrical interactions with its parent planet. Mars, on the other hand, tells a more cautionary tale. Today, Mars has no global magnetic field to speak of. It has only localized, remnant patches of crustal magnetism, fossilized magnetic fields that are locked into the ancient rocks of its crust. These are the ghosts of a magnetic field that Mars likely had in its distant past, when its core was still hot and molten. The loss of this global magnetic field, which probably shut down billions of years ago as the planet's core cooled and solidified, had catastrophic consequences. Without a magnetosphere to protect it, the solar wind has, over eons, stripped away the vast majority of Mars's once thicker atmosphere, transforming it from a world that may have once been warm and wet into the cold, dry, and barren desert we see today. Venus, Earth's twin in size and composition, presents another puzzle. Despite its similar size, Venus has no significant, internally generated magnetic field. This is likely due to its incredibly slow rotation. A day on Venus is longer than its year, which is not fast enough to drive the necessary churning motions in its core to create a dynamo. The study of these different planetary magnetic fields is a form of comparative planetology that allows us to understand the key ingredients necessary for creating and sustaining a habitable world. It tells us that a planet's magnetic field is not just a geological curiosity. It is a crucial component of its climate, its atmosphere, and its ultimate potential to harbor life. The Earth's magnetic field is not a static, unchanging entity. The geological record, preserved in the magnetic minerals of ancient lava flows, tells us a remarkable story. Our planet's magnetic field has, throughout its history, repeatedly and dramatically flipped its polarity. The North Magnetic Pole has become the South Magnetic Pole, and vice versa. These geomagnetic reversals are not instantaneous events. They are complex and often chaotic, processes that can take several thousand years to complete. During a reversal, the main dipole component of the Earth's field weakens significantly, and the field can become much more complex, with multiple temporary north and south poles scattered across the globe. The exact mechanism behind these reversals is still a subject of active research, but it is thought to be related to the complex, turbulent dynamics of the molten iron in the Earth's outer core. The geodynamo is not a steady, clockwork machine. It is a chaotic system. And like all chaotic systems, it is subject to sudden and dramatic shifts in its behavior. The last major reversal occurred about 780,000 years ago, and there is some evidence to suggest that we may be in the early stages of a new one, as the strength of the Earth's magnetic field has been observed to be decreasing over the last few centuries, and the North Magnetic Pole is currently wandering across the Arctic at a surprisingly rapid rate. The prospect of a geomagnetic reversal can sound alarming. What would happen to our technological civilization, so dependent on satellites and power grids, if our planet's magnetic shield were to weaken significantly for a few thousand years? And what would be the impact on life? The fossil record does not show any clear evidence of mass extinctions being correlated with past reversals, which suggests that the consequences may not be as catastrophic as one might imagine. Even during a reversal, the Earth is not left completely unprotected. A weaker, more complex magnetic field would still provide some shielding from the solar wind, and our atmosphere itself is a powerful secondary shield against cosmic radiation. But there would undoubtedly be challenges. The increased influx of energetic particles could pose a risk to our technological infrastructure and could lead to more frequent and spectacular auroral displays at lower latitudes. The study of geomagnetic reversals is a powerful reminder of the dynamic and sometimes unpredictable nature of our own planet. It is a story that is written in the rocks beneath our feet, a story of a planet that is constantly changing, constantly evolving, a story whose next chapter we may be living through right now. The journey into the heart of magnetism takes us from the familiar shield of our own planet to the grand cosmic forges where stars themselves are born. The Sun, the star at the center of our solar system, is a magnetic powerhouse. Its magnetic field is generated by a complex dynamo process, similar to Earth's, but driven by the turbulent, convective motions of the hot ionized gas, or plasma. That makes up its interior. This solar dynamo is not a steady process. It is a cyclical one, with the Sun's overall magnetic field flipping its polarity approximately every 11 years. This 11-year cycle is the driving force behind all of solar activity. The Sun's magnetic field is not a simple bar magnet-like dipole. It is a complex, twisted and ever-changing web of magnetic flux tubes that are constantly being stretched, sheared, and tangled by the Sun's differential rotation, the fact that its equator rotates faster than its poles. When these tangled magnetic field lines become too stressed, they can suddenly snap and reconnect, releasing a tremendous amount of energy in a violent, explosive event. These are solar flares, some of the most powerful explosions in our solar system. A large solar flare can release the energy equivalent of millions of hydrogen bombs in a matter of minutes, sending a burst of high-energy radiation and charged particles out into space. Sometimes, these magnetic reconnection events can also trigger a coronal mass ejection, a vast billion-ton cloud of magnetized plasma that is hurled out from the Sun's atmosphere at millions of kilometers per hour. If a CME is directed towards Earth, it can have a significant impact on our planet's magnetic environment, triggering powerful geomagnetic storms, beautiful auroral displays, and potentially disrupting our satellites, power grids, and communication systems. The dark, cooler regions we see on the Sun's surface, known as sunspots, are also a magnetic phenomenon. They are areas where intense, concentrated magnetic field lines are poking through the Sun's visible surface, inhibiting the flow of hot gas from the interior and causing the region to cool down. The number of sunspots on the Sun varies in a cyclical way, reaching a maximum every 11 years, in sync with the solar magnetic cycle. The study of the Sun's magnetic field is not just an academic exercise, it is a matter of practical importance, as space weather can have a real and sometimes disruptive impact on our technological society. But to truly understand the cosmic role of magnetism, we must journey even further out, into the vast, cold, and dark molecular clouds that are the stellar nurseries of our galaxy. It is here, in these seemingly serene and quiescent clouds of gas and dust, that magnetic fields play their most crucial and creative role as the silent and often unacknowledged midwives of star formation. The birth of a star begins with the slow gravitational collapse of a dense core within a molecular cloud. But this collapse is not a simple, unimpeded freefall. It is a complex and delicate dance between the inward pull of gravity and the outward push of other forces. And the most important of these is the magnetic field that threads through the cloud. The interstellar medium is not empty. It is filled with a weak, but pervasive, magnetic field. As a cloud of gas collapses under its own gravity, it pulls these magnetic field lines in with it, compressing and amplifying them. This creates a magnetic pressure that can resist the gravitational collapse, slowing it down and regulating the process. Without the moderating influence of magnetic fields, the gravitational collapse of a molecular cloud would be a much more rapid and chaotic affair, likely leading to the formation of a few very massive stars, rather than the rich diversity of stellar masses that we actually observe. The magnetic field acts as a kind of cosmic brake, ensuring that star formation is a slow, steady, and relatively efficient process. But the magnetic field does more than just resist the collapse. It also plays a crucial role in solving one of the key puzzles of star formation, the angular momentum problem. A collapsing cloud of gas, due to the conservation of angular momentum, should spin faster and faster as it shrinks, in the same way that an ice skater spins faster when she pulls her arms in. The amount of angular momentum in a typical molecular cloud core is so large that, if it were all conserved in the final star, the star would be spinning so fast that it would tear itself apart. Something must be getting rid of the excess angular momentum, and that something is the magnetic field. The magnetic field lines that are threaded through the collapsing core are also connected to the surrounding, more diffuse gas of the cloud. As the core spins up, it twists these magnetic field lines, creating a magnetic torque that transfers the angular momentum outwards from the rapidly spinning core to the more slowly rotating envelope. This process, known as magnetic braking, is incredibly efficient, and it is what allows the protostar to shed its excess angular momentum and to continue its slow, steady collapse into a stable, newly formed star. The influence of magnetism on the star formation process is visible in the very structure of the stellar nurseries themselves. High-resolution images of molecular clouds, particularly those taken in polarized light, reveal a stunning filamentary structure. These are not random, chaotic tendrils of gas. They are ordered, coherent structures, vast magnetic rivers that are shaped and confined by the interstellar magnetic field. The gas in these filaments is thought to be flowing along the magnetic field lines, channeling material from the diffuse, outer regions of the cloud into the dense, star-forming cores. The magnetic field acts as a cosmic scaffolding, guiding the flow of matter and providing the architectural blueprint for the entire star formation process. But the relationship between magnetism and the cloud is a complex one. While the magnetic field can channel the flow of the ionized component of the gas, the neutral component can, over long timescales, slowly drift across the magnetic field lines in a process known as ambipolar diffusion. This is a crucial step in the formation of a star, as it allows a dense core to decouple from the magnetic support of the larger cloud and to begin its final, inexorable gravitational collapse. The star formation process is a delicate interplay between the inward pull of gravity, the outward push of magnetic pressure, and the slow, patient drift of neutral matter through the magnetic web. The observational tools we use to study this invisible magnetic architecture are becoming increasingly powerful. By measuring the polarization of the faint, thermal radiation emitted by dust grains in molecular clouds, we can map the orientation of the magnetic field lines, as the elongated dust grains tend to align themselves with the local field. The Zeeman effect, the splitting of spectral lines in the presence of a magnetic field, provides a more direct, but much more challenging, way to measure the strength of the field itself. With new, powerful telescopes like the Atacama Large Millimeter/Submillimeter Array, we are now able to create stunning, high-resolution maps of the magnetic fields in nearby star-forming regions, providing a detailed, empirical check on our theoretical models. These observations are confirming the central, and often dominant, role of magnetism in the birth of stars. They are showing us a universe where the process of creation is not a simple matter of gravity, but a complex and beautiful dance between gravity, turbulence, and the silent, guiding hand of the magnetic field. The journey into the heart of cosmic magnetism takes us from the relatively gentle, organizing influence of the fields in stellar nurseries to the far more violent and spectacular realm of cosmic jets. These are some of the most powerful and enigmatic phenomena in the universe, narrow, highly collimated beams of plasma that are ejected from the vicinity of massive celestial objects at speeds approaching the speed of light. They are cosmic fire hoses of incredible power, capable of traveling for hundreds of thousands and even millions of light years. shaping the galaxies and the intergalactic medium through which they pass. And at the heart of every cosmic jet lies a powerful, twisted, and dynamic magnetic field. The formation of these jets is intimately tied to the process of accretion, the spiraling inflow of gas and dust onto a central, compact object. This can be a young, newly forming star, a dense, stellar remnant like a neutron star or a white dwarf, or, in the most spectacular cases, a supermassive black hole at the center of a galaxy. As this material spirals inwards, it forms a hot, dense, and rapidly rotating accretion disk, and it is from the inner regions of this chaotic, swirling maelstrom of plasma that the jets are born. The magnetic field is the key ingredient that channels and accelerates this outflow. The rapid rotation of the accretion disk, combined with the turbulent, convective motions within it, acts as a powerful dynamo, amplifying and twisting the magnetic field lines into a tightly wound, helical structure that extends outwards, perpendicular to the disk. These twisted, magnetic field lines act like a cosmic nozzle, a magnetic slingshot that grabs onto the charged particles of the plasma and flings them outwards at incredible speeds. The process of magnetic reconnection, where stressed and twisted magnetic field lines can suddenly snap and reconfigure themselves, is thought to be a key mechanism for releasing the immense amounts of energy that power these jets. The high-energy particles within the jets, spiraling around these powerful magnetic field lines, emit a strong, characteristic form of radiation known as synchrotron radiation. This radiation, which is most prominent at radio wavelengths, is the smoking gun signature of a cosmic jet, and it is what allows us to map their structure and to study their properties across the vast distances of the cosmos. The most powerful jets in the universe are those that are launched from the accretion disks around supermassive black holes at the centers of active galaxies. These are the quasars and radio galaxies, some of the most luminous objects in the cosmos. Their jets can be truly colossal, extending far beyond the confines of their host galaxy and plowing into the tenuous, hot gas of the intergalactic medium. As they do so, they create vast, expanding lobes of radio-emitting plasma, giant structures that can be hundreds of thousands of light years across. These jets have a profound and transformative impact on their environment. The immense amount of energy and momentum they carry can heat up the surrounding gas, preventing it from cooling and forming new stars. This jet feedback is now thought to be a crucial mechanism in regulating the growth of massive galaxies, explaining why the most massive galaxies in the universe seem to have stopped forming stars billions of years ago. The jets from their central, supermassive black holes have effectively sterilized them, cutting off their supply of cold, star-forming gas. But jets are not just found in the most massive and exotic systems. We also see them on a much smaller scale, associated with the birth of ordinary sun-like stars. These protostellar jets, often referred to as Herbig-Haro objects, are a crucial part of the star formation process. They are thought to be the primary mechanism by which a young upforming star sheds its excess angular momentum, allowing it to continue its gravitational collapse. The outflowing jet carries away the spin, allowing the central protostar to continue to grow in mass. The study of cosmic jets is a field that brings together many different areas of astrophysics, from plasma physics and magnetohydrodynamics to general relativity and high-energy particle physics, and our observational tools are becoming increasingly powerful. With arrays of radio telescopes like the Very Large Array and the Future Square Kilometer Array, we can create stunning, high-resolution images of the jets and their interaction with their environment. With X-ray and gamma-ray telescopes in space, we can study the high-energy particles within the jets and the processes that accelerate them to near the speed of light. And with the Event Horizon Telescope, a global network of radio telescopes that can achieve an angular resolution equivalent to seeing an orange on the surface of the moon. We are now able to image the very base of the jet, right at the edge of the event horizon of a supermassive black hole. These observations are providing us with an unprecedented view of one of nature's most extreme and powerful phenomena, a phenomenon that is driven, at its core, by the beautiful, complex, and violent dance of matter and magnetism in the heart of the cosmos. The universe is a gallery of extremes, and nowhere is this more apparent than in the dense, crushed remnants of dead stars. It is in these stellar graveyards that magnetic fields can reach strengths that are almost beyond our comprehension, creating some of the most exotic and fascinating objects in the cosmos. A white dwarf is the final, evolutionary state of a star like our Sun, after it has exhausted its nuclear fuel. It sheds its outer layers to form a beautiful, glowing planetary nebula, leaving behind a hot, dense core of carbon and oxygen, about the size of the Earth, but with the mass of the Sun. Many white dwarfs have surprisingly strong magnetic fields, ranging from thousands to even billions of times the strength of Earth's magnetic field. These fields are thought to be a fossilized remnant of the magnetic field of the progenitor star, compressed and amplified during the star's collapse. These strong fields have a profound effect on the white dwarf's atmosphere, distorting the energy levels of the atoms and creating a unique and very complex spectral signature, a phenomenon known as the Zeeman effect. By carefully analyzing this spectral splitting, astronomers can map the strength and structure of the magnetic fields on the surfaces of these dead stars. But the story of magnetic compact objects gets even more extreme when we consider the fate of more massive stars. A star that is several times more massive than the Sun will end its life in a spectacular supernova explosion, its core collapsing under its own immense gravity to form a neutron star. These are objects of incredible density, packing more than the mass of the Sun into a sphere that is only about 20 kilometers in diameter. A single teaspoon of neutron star material would weigh billions of tons. As the core collapses, the conservation of angular momentum causes the neutron star to spin incredibly rapidly, often hundreds of times per second. And the conservation of magnetic flux causes its magnetic field to be amplified to truly staggering levels, typically around 1 trillion times the strength of Earth's field. If the neutron star's magnetic axis is misaligned with its rotation axis, it will sweep a powerful beam of electromagnetic radiation across space, like a cosmic lighthouse. If this beam happens to sweep across the Earth, we see it as a regular, pulsating signal, and we call the object a pulsar. Pulsars are some of the most precise clocks in the universe, and they are powerful probes of the interstellar medium and of the laws of gravity in extreme conditions. But the real drama unfolds when these magnetic, compact objects are not alone, but are part of a binary star system. If a white dwarf or a neutron star is in a close orbit with a normal companion star, its powerful gravity can pull material from the companion, creating an accretion disk of hot, spiraling gas. The interaction between this infalling material and the magnetic field of the compact object creates some of the most energetic and dynamic phenomena in the universe, in a system known as a magnetic cataclysmic variable. The magnetic field of the white dwarf is so strong that it prevents the formation of a normal accretion disk. Instead, the infalling material is channeled directly along the magnetic field lines, forming a stream or an accretion column that crashes onto the magnetic poles of the white dwarf, creating an intensely hot X-ray emitting shock. In binary systems containing a neutron star, the infalling material can accumulate on the surface, its temperature and density increasing until it triggers a runaway thermonuclear explosion, a powerful burst of X-rays that can be seen across the galaxy. But the most extreme magnetic objects in the universe are the magnetars. These are a rare and still not fully understood type of neutron star with magnetic fields that are up to 1,000 times stronger than those of a typical pulsar, reaching strengths of up to 1 quadrillion times that of the Earth. These are the strongest magnetic fields known to exist in the cosmos. The energy stored in these immense fields is so great that it can cause the solid crust of the neutron star to crack and shift in a violent starquake. These starquakes can trigger a catastrophic release of magnetic energy, creating a giant flare, a burst of gamma rays and X-rays that can, for a brief moment, outshine all the other sources in our galaxy combined. A giant flare from a magnetar in our own galaxy, if it were directed towards us, could have a significant impact on the Earth's upper atmosphere, even from a distance of tens of thousands of light years. Magnetars are also thought to be a leading candidate for the source of the enigmatic fast radio bursts, the powerful millisecond-long bursts of radio waves that are being detected from distant galaxies, the extreme and often violent. Behavior of these magnetic compact objects is a powerful testament to the central role that magnetism plays in the high-energy universe. They are natural laboratories for studying the behavior of matter and energy under conditions of extreme density, gravity, and magnetism, conditions that we can never hope to replicate on Earth, and they are a reminder that the universe is full of objects that are far stranger, more powerful, and more beautiful than our classical intuition could have ever imagined. Magnetars are the undisputed kings of cosmic magnetism, a rare and enigmatic class of neutron star whose magnetic fields are so titanically powerful that they warp the very fabric of reality around them. Born from the fiery death of massive stars in supernova explosions, these objects are a testament to the extremes that nature can achieve. The process of their formation is a lesson in the conservation laws of physics. As the core of a massive star collapses under its own gravity, from a size of hundreds of thousands of kilometers down to a sphere just 20 kilometers across, it conserves its angular momentum, causing it to spin up to incredible speeds, and it conserves its magnetic flux, compressing the magnetic field of the progenitor star to unimaginable densities. While all neutron stars are highly magnetized, it is thought that only those that are born with a particularly rapid initial spin can drive a powerful enough dynamo mechanism in their turbulent, convective interiors to amplify the magnetic field to the quadrillion Gauss levels that define a magnetar. This is a field that is 1,000 times stronger than that of a typical pulsar, and 1,000 trillion times stronger than the magnetic field of our own Earth. A magnetic field of this magnitude is so strong that it has profound and bizarre effects on the physics in its vicinity. It would distort the very shape of the atoms on the magnetar's surface, stretching them into long, thin needles aligned with the field lines. It would cause the vacuum of space itself to become birefringent, a quantum electrodynamical effect where the vacuum acts like a crystal, splitting a beam of light into two different polarizations. And it is the primary source of the magnetar's own extraordinary energy output. Unlike a normal pulsar, which is powered by its rotational energy, a magnetar is powered by the decay of its immense magnetic field. The energy stored in this field is so vast that it can cause the solid, crystalline crust of the neutron star to periodically crack and buckle in a violent event known as a starquake. This is analogous to an earthquake on Earth, but on a scale of energy and violence that is almost beyond comprehension. These starquakes can trigger a catastrophic and sudden reconfiguration of the external magnetic field, leading to a giant flare, a burst of high-energy gamma rays and X-rays that can release more energy in a fraction of a second than our sun will emit in 100,000 years. In 2004, a giant flare from the magnetar SGR 1806-20, located about 50,000 light-years away on the other side of our galaxy, was so powerful that it measurably disturbed the Earth's ionosphere. If such an event were to occur from a magnetar much closer to us, the consequences could be significant. The intense and often violent activity of magnetars also explains their relatively short observable lifetimes. The decay of their magnetic field, which powers their outbursts, also causes them to spin down much more rapidly than a normal pulsar. A typical magnetar will slow its rotation from milliseconds to several seconds in just a few thousand years. After about 10,000 years, its magnetic field has likely decayed to a point where it is no longer active, and the magnetar becomes a quiescent and largely invisible neutron star. This short lifetime is one of the reasons why magnetars are so rare. We can only see them during the brief and spectacular period of their youthful activity. The study of these extreme objects has been revolutionized by our high-energy telescopes in space, like the Chandra X-ray Observatory and the Neil Gehrels Swift Observatory. These instruments are able to detect the frequent, smaller bursts and the rare, giant flares from magnetars, allowing us to study the dynamics of their magnetic fields and the physics of their violent outbursts. These observations are providing crucial data to test our theoretical models of magnetar physics, and they are also shedding light on one of the most exciting new mysteries in astronomy, the origin of fast radio bursts. FRBs are intense, millisecond-long bursts of radio waves that are being detected from distant, extragalactic sources. Their origin is unknown, but a leading candidate is a young active magnetar. In 2020, a powerful radio burst, with properties very similar to an FRB, was detected from a magnetar within our own Milky Way galaxy, providing the first, strong, smoking gun evidence for this connection. It seems likely that at least some, and perhaps all, FRBs are the extragalactic cousins of the giant flares we see from the magnetars in our own cosmic backyard. Magnetars are more than just astronomical curiosities. They are natural laboratories for probing the limits of physics. Their immense magnetic fields allow us to study the behavior of matter and radiation under conditions of extreme energy and density, conditions that are far beyond anything we can ever hope to create on Earth. They are a window into the world of quantum electrodynamics in the strong field regime, where the vacuum itself becomes a dynamic, physical medium, and they are a powerful reminder that the universe is a place of constant and often violent transformation, a place where the death of a star can give birth to an object of such extreme and beautiful strangeness that it challenges the very boundaries of our scientific understanding. The centers of galaxies are the cosmic crucibles where the most extreme forces of nature are at play. And at the very heart of most, if not all, large galaxies lies a supermassive black hole, a gravitational behemoth with a mass of millions, or even billions, of times that of our Sun. These objects are not just passive gravitational sinks, they are dynamic, powerful engines that can have a profound and transformative impact on the evolution of their entire host galaxy. And the key to unlocking their power, the medium through which they exert their influence, is the magnetic field. A supermassive black hole, on its own, is a relatively simple object, described only by its mass and its spin. The real action happens in the accretion disk that often surrounds it, a swirling, chaotic vortex of gas, dust, and shredded stars that are being pulled in by the black hole's immense gravity. As this material spirals inwards, it is heated to millions of degrees by friction, creating an intensely luminous source of radiation that can, in the case of a quasar, outshine all the stars in the host galaxy combined. And this accretion disk is a magnetic cauldron. The turbulent, churning motions of the hot, ionized plasma in the disk act as a powerful dynamo, amplifying and tangling the magnetic field lines, creating a complex and dynamic magnetic structure that is intimately tied to the process of accretion itself. It is this magnetic field that is thought to be the primary mechanism for launching the spectacular relativistic jets that we see emerging from the centers of many active galaxies. in a process that is still not fully understood, but is likely related to the twisting of magnetic field lines by the rotating accretion disk and the spinning black hole itself. A portion of the infalling material can be grabbed by the magnetic field and accelerated outwards, perpendicular to the disk, at speeds approaching the speed of light. The Blandford-Zajac mechanism is a leading theoretical model for how this can happen. It proposes that the rotational energy of the spinning black hole itself can be extracted by the magnetic field lines that thread its event horizon, providing a powerful source of energy to drive the jets. In this picture, the magnetic field is a kind of cosmic transmission belt, converting the gravitational and rotational energy of the black hole system into the kinetic energy of a powerful collimated outflow. We are now, for the first time in history, able to image the immediate vicinity of a supermassive black hole and to directly map the structure of its magnetic field. The Event Horizon Telescope, a global network of radio telescopes that uses a technique called very long baseline interferometry to create a virtual, Earth-sized telescope, has produced stunning images of the shadow of the supermassive black holes at the center of our own Milky Way galaxy and the giant elliptical galaxy M87. And by measuring the polarization of the radio waves emitted by the hot plasma around the black hole, the EHT has been able to create the first ever maps of the magnetic field structure right at the edge of the event horizon. These images have revealed a swirling, ordered pattern of magnetic field lines, confirming the theoretical predictions and providing a stunning, direct view of the magnetic engine that is thought to be responsible for launching the M87 jet. The influence of these black hole-driven, magnetized jets extends far beyond the galactic nucleus. They are a powerful form of feedback, a mechanism by which the central black hole can regulate the growth of its entire host galaxy. The jets plow into the interstellar medium of the galaxy, creating vast, expanding bubbles of hot gas and driving powerful shock waves that can heat up the surrounding cooler gas. This can have a profound effect on the process of star formation. Stars are born from the collapse of cold, dense molecular clouds. If the gas in a galaxy is heated up by the energy injected from a central jet, it can be prevented from cooling and collapsing, effectively shutting down or quenching the process of star formation. This jet mode feedback is now thought to be one of the key reasons why the most massive galaxies in the universe are no longer forming stars. They are red and dead, their star formation having been quenched billions of years ago by the powerful and ongoing activity of their central, supermassive black holes. The magnetic field is the crucial ingredient in this process, as it is what allows the energy and momentum of the jet to be efficiently coupled to the surrounding gas. The interplay between the growth of a supermassive black hole and the evolution of its host galaxy is one of the most active and exciting areas of modern astrophysics. It is a story of co-evolution, of a deep and intimate connection between the smallest and the largest scales of a galaxy. And it is a story that is, at its heart, a magnetic one. The magnetic fields in the accretion disk launch the jets. The jets regulate the star formation in the galaxy. The star formation provides the fuel that feeds the black hole, and the cycle continues. It is a beautiful, self-regulating cosmic ecosystem, a dance of gravity, gas, and magnetism that has shaped the appearance and the history of every large galaxy in the universe. Our own Milky Way is a relatively quiet galaxy at present, its central black hole in a state of slumber, but it has likely gone through more active jet-producing phases in its past, and it will likely do so again in the future. The study of the magnetic fields around black holes is not just about understanding these exotic, extreme objects. It is about understanding the grand, cosmic story of which we are a part. The story of how galaxies and the stars and planets within them are born, how they live, and how they die. The influence of magnetism is not confined to the dense, active environments of stars and galaxies. It extends out into the vast, tenuous, and seemingly empty spaces between them. The universe, on its largest scales, is structured as a cosmic web, an intricate, interconnected network of vast filaments of galaxies and dark matter, separated in immense, almost empty voids. And this cosmic web is not just a gravitational structure, it is a magnetized one. The space between the galaxies, the intergalactic medium, is permeated by a weak but pervasive magnetic field. The existence of these intergalactic magnetic fields is a profound and puzzling discovery. Their strength is incredibly small, typically 1 billion times weaker than the magnetic field of the Earth, but they extend over millions, and even billions, of light years, making them the largest coherent magnetic structures in the universe. The origin of these cosmic-scale magnetic fields is one of the great unsolved mysteries of modern cosmology. Where did they come from? One possibility is that they are of astrophysical origin, that they were seeded by the magnetic fields that were generated within the first stars and galaxies and then ejected into the intergalactic medium by powerful galactic winds. Outflows of gas driven by supernova explosions and the activity of central black holes over cosmic time. These ejected fields would have been stretched and sheared by the large-scale flows of the expanding universe, eventually filling the vast spaces of the cosmic web. Another, more exotic possibility is that they are of primordial origin, that they were created in the very early universe, long before the first stars and galaxies ever formed. There are several proposed mechanisms for how this could have happened. During the period of cosmic inflation, quantum fluctuations in the electromagnetic field could have been stretched to cosmological scales, creating a primordial magnetic field. Or, during one of the phase transitions of the early universe, such as the electroweak transition or the QCD transition, bubbles of a new vacuum state could have formed, and the collisions between these bubbles could have generated magnetic fields. Distinguishing between these astrophysical and primordial origin scenarios is a major goal of modern cosmology. A primordial magnetic field would have a different statistical signature than one that was generated later, and this could, in principle, be detected in the subtle patterns of the cosmic microwave background or in the large-scale distribution of galaxies. The detection of a primordial magnetic field would be a discovery of monumental importance, as it would provide a direct window into the physics of the universe in its first fleeting moments. Within the dense, hot environments of galaxy clusters, the largest gravitationally bound structures in the universe, the magnetic fields are significantly stronger than in the general intergalactic medium, reaching strengths of a few microgauss, similar to the field in our own Milky Way. These intracluster magnetic fields are thought to be amplified by the turbulent, churning motions of the hot X-ray emitting gas that fills the space between the cluster galaxies. The constant motion and merging of galaxies within the cluster acts as a powerful, large-scale dynamo, tangling and amplifying the magnetic field lines. These cluster magnetic fields play a crucial role in the physics of the intracluster medium. They can influence the transport of heat, potentially solving the long-standing cooling flow problem. The mystery of why the gas in the centers of many clusters is not cooling and forming stars as rapidly as simple models would predict. They can also accelerate cosmic ray particles to incredible energies, creating the vast, diffuse radio halos and relics that are observed in many galaxy clusters. The study of these cosmic-scale magnetic fields is incredibly challenging. They are too weak to be detected directly. Instead, we must rely on indirect methods. The most powerful of these is Faraday rotation. When a beam of polarized light, such as the radio waves from a distant quasar, passes through a magnetized plasma, its plane of polarization is rotated, The amount of this rotation depends on the strength and orientation of the magnetic field along the line of sight. By observing the Faraday rotation of many background sources seen through a galaxy cluster or a filament of the cosmic web, astronomers can create detailed, three-dimensional maps of the magnetic field structure. The next generation of radio telescopes, particularly the square-kilometer array, will revolutionize this field. With its unprecedented sensitivity and its ability to survey vast areas of the sky, the SKA will be able to map the cosmic magnetic web with a detail and a depth that is currently unimaginable. It will allow us to trace the magnetic fields from the hearts of galaxies out into the intracluster medium and along the vast filamentary structures that connect them. This will provide a completely new and fundamentally important view of the universe. It will transform our understanding of the cosmic web from a simple, gravitational structure into a dynamic, magnetized ecosystem, a place where the flow of matter and energy is governed by the complex and beautiful interplay between gravity and magnetism. The invisible, magnetic threads of the cosmos are what bind it together, and we are, for the first time, beginning to learn how to see them. The study of cosmic magnetism is a field that is driven by a constant and creative interplay between theoretical modeling, numerical simulation, and observational astronomy. Because magnetic fields are invisible, we must rely on a variety of clever, indirect techniques to detect their presence and to map their structure. One of the most important of these, as we have seen, is the observation of synchrotron radiation. When a high-energy charged particle, like an electron, spirals around a magnetic field line at a speed close to the speed of light, it emits a powerful beam of electromagnetic radiation. This synchrotron emission is a characteristic fingerprint of a magnetized, high-energy environment, and it is most prominent at radio wavelengths. By creating detailed, high-resolution maps of the synchrotron emission from objects like supernova remnants, radio galaxies, and galaxy clusters, radio astronomers can trace the structure of the magnetic fields and study the properties of the high-energy particles within them. The polarization of this synchrotron light provides even more information, as it is directly related to the orientation of the magnetic field lines. To carry out these observations, astronomers use some of the most powerful and sophisticated telescopes on Earth. Ground-based radio interferometers, like the Very Large Array in New Mexico and the Low Frequency Array in Europe, consist of many individual radio antennas spread out over large distances. By combining the signals from these antennas, they can achieve an angular resolution that is equivalent to a single telescope many kilometers in size, allowing them to create incredibly detailed images of the radio sky. In the millimeter and submillimeter part of the spectrum, the Atacama Large Millimeter Submillimeter Array in Chile, a powerful interferometer situated high in the Andes Mountains, has revolutionized our view of the cold, dusty universe where stars and planets are born. ALMA's stunning images of protoplanetary disks and molecular clouds have revealed the intricate, filamentary structures that are shaped by magnetic fields, providing a direct view of the magnetic architecture of star formation. But the future of radio astronomy and of cosmic magnetism research lies with the square-kilometer array. This is not a single telescope, but a next-generation global observatory, a network of thousands of radio dishes and millions of low-frequency antennas that will be spread across 2 continents, in South Africa and Australia. When completed, the SKA will be the largest and most sensitive radio telescope ever built. It will have a collecting area of a square kilometer, and it will be able to survey the sky thousands of times faster than any existing instrument. The SKA will be a magnetic field machine. Its unprecedented sensitivity will allow it to detect the faint, polarized signals from the most distant galaxies, providing a map of how the magnetic fields in galaxies have evolved over cosmic time. It will be able to map the Faraday rotation of thousands of background sources, creating a three-dimensional tomographic map of the magnetic field in the cosmic web itself, allowing us to test our theories of the origin of cosmic magnetism. And it will be a powerful tool for studying transient magnetic phenomena, like fast radio bursts and the mergers of neutron stars.